Night falls on an ancient plain beneath a moonless sky. Overhead, a river of stars spills across the darkness. The Milky Way in all its glory, unmarred by any earthly light. In this primeval silence, the heavens are a tapestry of glittering lights. Each pinprick of starlight twinkles in the cool air, and in the stillness, one can almost feel the turning of the earth beneath that vast dome. Under these ancient skies, our distant ancestors gathered around gentle fires and gazed upward in wonder. With no scientific instruments, and only their eyes and imagination, they wove stories into the patterns they saw above. The stars became gods, heroes, animals, constellations connecting one bright dot to another across the night. The great band of the Milky Way was a cosmic river or a pathway of spirits, its soft, luminous glow inspiring both awe and comfort. From horizon to horizon, the night sky was a faithful clock and compass. The changing positions of stars signaled the passing of seasons and the approach of dawn. The moon, cycling from slender crescent to full brilliance and back, marked the rhythm of months and tugged gently at the oceans. And among the countless stars, a few were different. Tiny wandering lights that moved against the starry background, predictably, yet mysteriously. These wandering stars, planets, captured human curiosity, even if their true nature was not yet known. In different cultures, these wandering points of light were given names of gods and heroes. Bright Venus was a goddess of love and beauty, ruddy Mars, a symbol of war, golden Jupiter, king of the heavens, and pale Saturn, ancient lord of time. Their movements against the fixed stars were charted by priests and early astronomers, and monuments of stone were raised to honor and track the sky. Across the world, structures like Stonehenge and the pyramids were aligned with the rising sun or certain stars, reflecting the deep importance of the heavens to those who built them. Under the ancient sky, time felt eternal. Each night the cosmos performed its silent symphony, encouraging questions about what those distant lights were and what they meant. In the crisp air of midnight, one could sense both the profound stillness and the subtle motions of the heavens. It was a time of innocence and curiosity, when the universe was a vast, unknown canvas, and our ancestors could only dream of what lay beyond the points of light. As the long night passed, slowly, a new glow would touch the eastern sky. Stars would fade one by one as a greater light announced itself. In the hush before dawn, a chill might hang in the air, yet on the horizon, the first rays of morning began to bloom. The ancient stargazers turned toward the growing radiance, toward the rising sun that would soon dominate the sky and wash away the stars. The sun ascends, flooding the sky with gentle gold. Its warmth stirs the cool morning air and awakens life below. This radiant star that banishes the night is more than a light in our sky. It is the heart of our solar system. In the stillness of dawn, we feel its life-giving touch, yet few truly grasp its immense power and scale. High above, the sun appears a perfect golden disk, but up close, it is a roiling sphere of hot plasma over 1 million kilometers across. Deep in its core, unimaginable pressure and heat fuse hydrogen into helium, releasing energy that slowly travels outward. After a journey of thousands of years through the sun's dense interior, that energy emerges at the surface as sunlight. Once free, each particle of light races through space at 300,000 kilometers per second, across the void toward the waiting worlds. It takes about 8 minutes for the sun's light to reach Earth, crossing 150 million kilometers of emptiness to arrive each morning. For over 4.5 billion years, the sun has burned steadily, anchoring the family of planets in its gravitational embrace. Its light and heat define the very conditions for life on Earth, and its gravity guides the paths of worlds, asteroids, and comets alike. Every sunrise ties us to an ancient ritual that has been ongoing since before humans walked the Earth, the turning of our planet toward our star once more. Yet the sun is not a static beacon. It lives and breathes in its own way. Dark sunspots freckle its surface from time to time, cooler islands amid the boiling heat. Great arcs of solar material rise and fall, loops of glowing plasma tracing magnetic fields above the sun's surface. Occasionally, the sun flares with sudden intensity, ejecting clouds of charged particles outward into space. This ceaseless activity is like a slow heartbeat and gentle breath, felt across the solar system as the solar wind, a continuous, faint breeze of particles that drifts outward and ultimately defines the boundary of our star's influence. From Earth, the sun's brilliance by day hides the wider cosmos, yet reminds us that the countless stars at night are suns themselves, very far away. Our sun is but one ordinary star among billions in the galaxy, but to us, it is uniquely precious. It is the source of almost all energy for the life on our planet. Ancient cultures revered it as a deity. The Egyptians called it Ra, and the Greeks imagined Helios riding a golden chariot across the sky. Modern science reveals it as a giant nuclear furnace in space. Both views capture an aspect of its truth. Giver of life, mighty and enduring, yet one day destined to change. In the extremely distant future, billions of years from now, the sun will exhaust its current fuel. It will swell into a red giant, enveloping its innermost planets and bathing the edges of the solar system in a ruddy glow. Eventually, it will cast off its outer layers and dwindle to a hot, dense ember called a white dwarf. But for now, and for countless millennia to come, our sun will continue to shine steadily, a warm, guiding star nurturing its orbiting worlds. Basking in the sun's light, one world in particular has flourished with life, our Earth, a blue oasis amid the dark. Seen from space, Earth shines with a tranquil blue hue. White swirls of cloud dance over oceans and continents, and the planet's surface glints where sunlight touches water. This is our home, a vibrant sphere teeming with life, suspended in the void. To any cosmic traveller, Earth would stand out as a living world, its air and oceans in motion, its colours ever-changing with swirling clouds and seasonal greens and browns. Earth orbits the sun at just the right distance for liquid water to persist, a fortunate position in what scientists often call the Goldilocks zone, neither too hot nor too cold. In this narrow band, our planet's water can remain liquid, gathering into vast oceans that cradle life. Under the sun's gentle warmth, life on Earth has flourished for billions of years, evolving in complexity from simple single-celled organisms into the rich tapestry of plants and animals we know today. Lush green forests, shimmering blue seas, and golden deserts, all are nurtured by sunlight and water, all part of Earth's delicate biosphere. From microscopic algae to towering redwoods, from the tiniest insect to the great whales, life fills every corner of our world. Our planet hums with the music of life, making it unique in the solar system, as far as we know. From the vantage of space, one can see the thin halo of atmosphere encasing Earth, a fragile, glowing film of air that protects and sustains everything living. This atmosphere filters the sun's harsher radiation, burns up many incoming meteoroids, and circulates air and water to soften extremes of climate. It also scatters sunlight to paint our skies blue and our sunsets rose and orange. Beneath this blanket of air, countless forms of life thrive in an intricate balance, largely unaware of the silent vacuum just beyond. All the while, Earth rotates once each day, giving us the cycle of day and night, as it has since time immemorial. Earth's constant companion, the Moon, hangs nearby in space, a grey, cratered orb locked in an eternal dance with our planet. The Moon formed in violence long ago, likely when a Mars-sized protoplanet collided with the early Earth, blasting out debris that coalesced into our Moon. Out of chaos came this serene satellite. Now the Moon's presence is gentle and stabilizing. It orbits Earth every 27 days, always showing the same face to us, as if gazing forever at its parent world. In the night sky, the Moon's reflected glow has guided and comforted humanity for millennia, a silver lantern waxing and waning through its familiar phases. On the Moon's surface, the landscape is stark and silent. Without air or water, there is no sound and no weather, only ancient dust and the record of eons of meteoric bombardment etched into countless craters. The dark patches we see from Earth are vast plains of solidified lava from billions of years ago, and the bright highlands are older crust pitted by innumerable impacts. The Moon is a world frozen in time, preserving the early history of the solar system on its face. When we look at its softly glowing disk, we see a memory of our own planet's distant past. Yet in that stillness, the Moon gently tugs at Earth across the void. Its gravity pulls on our oceans, causing the rhythmic rise and fall of tides. Since the earliest life ventured onto land, those tides have been a subtle clock of nature. The Moon's steady gravitational presence also serves as an anchor on Earth's axis, keeping our planet's tilt, and thus our seasons, relatively stable over long ages. Without the Moon's calming influence, Earth's tilt might wander, leading to wild swings in climate over eons. The Moon, by simply existing beside us, has helped create the stable environment in which life could develop and thrive. Over the ages, the Moon has been a source of wonder and inspiration. It was once unreachable, a distant lantern in the sky, until in the 20th century, humans finally journeyed across the 250,000 miles of space to set foot on its surface. When astronauts first stood on the Moon's powdery soil, they looked up and saw Earth rising above the barren horizon, a delicate blue marble floating in blackness. In those moments, two worlds were connected by human presence. The Moon, once the subject of poems and dreams, became a place we had touched with our own hands. Those voyages lasted only a brief time, but the image of Earth from the Moon's perspective profoundly influenced humanity's view of our home. It reminded us that beyond our borders lies the great expanse of space, inviting us outward. Earth and Moon are bound together by invisible threads of gravity, pirouetting around a common center as they travel in tandem around the Sun. In the silence of space, our planet and its Moon move in harmony, a cosmic duet set against the starry background. This duet reminds us that even a planet as singular as ours is not truly alone. we share our path around the sun with our lunar companion, two partners in an elegant celestial dance. While Earth and the Moon serenely circle one another under the sun's embrace, closer to the sun lie two other rocky worlds that have their own tales to tell, worlds of extremes and mystery, often hidden in the sun's glare. Mercury, the innermost planet, is a world of extremes. It is a small, rocky globe pockmarked with craters, resembling Earth's moon in appearance. There are no flowing rivers or whispering winds on Mercury, only a barren surface that bears the scars of countless meteor impacts. Circling closest to the sun, Mercury completes a swift orbit in just 88 days. Daylight on Mercury brings searing heat under a sun that looms more than 3 times larger in its sky than what we see from Earth. On the sunlit side, the airless ground bakes to temperatures above 400 degrees, hot enough to melt lead, and the rocks glow under the relentless glare. Mercury's surface is a battered, scorched landscape, illuminated by a sun far more intense than we experience. Yet Mercury spins slowly on its axis, creating an unusual day-night rhythm. A single day on Mercury, from one sunrise to the next, lasts 2 entire Mercury years. For months on end, the sun hangs in Mercury's sky, blazing without respite and baking the ground. Then comes an equally long night of deep cold. Without any atmosphere to hold in the heat, Mercury's surface plummets to 180 degrees under an endless starry night. The contrast is stark and dramatic, from furnace-like days to frigid nights. Only in craters near Mercury's poles, where sunlight never reaches, does some water ice persist in eternal shadow, a surprising touch of frost in a world so close to the sun. With no air to scatter light, Mercury's sky remains black even at noon. The sun's brilliance dominates overhead, but beyond the blinding solar disk, the heavens are dark and filled with unblinking stars. It is a silent, airless world. Mercury's gravity, only about a third of Earth's, is too weak to hold on to an atmosphere under the sun's onslaught. Because it stays so near the sun from our viewpoint, Mercury often hides in the solar glare. For centuries it was challenging to observe. Early astronomers caught only fleeting glimpses of its cratered face during twilight hours. Only in recent decades, with spacecraft visits, have we seen Mercury's surface in detail. A rocky, cratered globe, not unlike our moon. Inside this tiny planet lies an oversized core of iron, Mercury's iron heart. In fact, Mercury's core makes up most of its interior, and it generates a surprisingly strong, albeit still small, magnetic field. This is an unexpected trait for such a diminutive world, and hints that parts of Mercury's core might remain molten, churning slowly and powering a magnetism that envelops the planet in a miniature magnetic bubble. Mercury, small as it is, still clings to some of the inner workings of a much larger planet. Farther out, the second planet from the Sun holds a very different mystery. Venus, named for the goddess of love and beauty, shines brilliantly in Earth's sky, often the brightest object after the Sun and Moon. Shrouded in thick, reflective clouds, Venus gleams like a steady beacon in the dawn or dusk, earning nicknames like the Morning Star and Evening Star. To the eye, it is beautiful, an ivory disk in a telescope, a jewel in the sky. But this beauty is deceiving, for beneath those golden white clouds lies an extreme and hostile realm. Venus is nearly the same size and mass as Earth, making it our planet's twin in some respects. In reality, it is a twisted twin, a vision of what Earth might look like under vastly different circumstances. The atmosphere of Venus is a dense cauldron of carbon dioxide, laced with clouds of sulfuric acid. At the surface, the pressure is crushing, around 90 times the pressure at Earth's sea level, akin to being nearly a kilometre under the ocean on Earth. This thick CO2 atmosphere has trapped heat in a runaway greenhouse effect, leading to surface temperatures around 465 degrees Celsius, hot enough to melt lead and hotter even than Mercury's daytime. Day or night, the heat barely varies, for the dense atmosphere distributes it evenly around the globe. The landscape bakes under a smothering, pale orange sky. What's more, Venus rotates to a different beat. It spins backward, opposite the direction of Earth's rotation, and does so extremely slowly. A single day on Venus, one full rotation, takes about 243 Earth days, which is actually longer than Venus's year of 225 days. The Sun, if one could see it through the perpetual clouds, would appear to rise in the west and set in the east, taking months to creep across the sky. In practice, the thick cloud cover means day on Venus is a perpetual murky twilight. Standing on Venus's surface, one wouldn't see the sun itself, just a diffuse orange glow filtering through heavy clouds. The sky would press down in every direction with a hazy reddish light. It would be like dusk on Earth, but unbearably hot and oppressive, with the weight of an ocean overhead. The surface of Venus is dry, barren, and rocky. There are no oceans. Any water boiled away eons ago. The terrain is a vast volcanic plain with rolling highlands and thousands of volcanoes, great and small. Spacecraft radar mapping has revealed mountains and impact craters and features that hint at tectonic stresses. Maxwell Montes, the tallest mountain on Venus, soars higher than Mount Everest. The ground is covered in volcanic rock, and in some cooler highland areas, strange substances like metallic frost, compounds of lead and bismuth, may precipitate out of the air, coating mountaintops with a dull metallic sheen. It is a vision of hell cloaked in clouds. Occasional lightning flickers within Venus's clouds, illuminating the gloom with brief electric blue flashes. The air, if we could breathe it, would taste of acid and brimstone. For a long time, Venus was an enigma. Its opaque clouds concealed its surface completely from human eyes. Not until the 20th century did radar and spacecraft pierce the veil, revealing the tortured landscape beneath. We found impact craters, giant volcanoes, and endless volcanic plains. We also found that Venus's climate had spiraled into a catastrophic greenhouse state. In studying Venus, we learned how delicate a planet's climate balance can be, and how a world so similar to Earth in size can take a very different path. Venus showed us a possible fate to avoid, a reminder that a planet's environment is not guaranteed to remain friendly. In its extremes, Venus taught us both the marvel and the danger of planetary evolution run awry. Mercury and Venus, the two innermost planets, illustrate the extremes of what rocky worlds can become. One is a tiny, baked ball of rock with hardly any atmosphere. The other, a nearly Earth-sized planet with an atmosphere so thick and hot it would instantly crush and suffocate any earthly life. Both orbit close to the sun's hearth, and both are utterly hostile to life as we know it. And yet, seen from afar, for millennia, they were simply wandering stars that our ancestors watched with wonder, bright points of light moving against the night sky, never suspecting the true nature of the inhospitable landscapes hidden beneath their brilliance. Leaving behind the scorching heat of Venus and the sun-blasted surface of Mercury, we journey outward again. Beyond Earth's orbit, beyond the warm glow of the inner solar system, lies a cold, rust-coloured world that has long captured human imagination. A lonely red planet, quiet and desolate, waiting in the darkness. Mars emerges in Earth's night sky as a faint but distinct red-orange dot. But up close, it is a rust-hued world of silent deserts. The fourth planet from the Sun, Mars is smaller than Earth, about half its diameter, and is now a cold, arid realm. Its surface is coated in iron-rich dust that gives the planet its distinctive ruddy colour. To the eye through a telescope, Mars shows subtle dark markings and bright polar caps that grow and shrink with the seasons, hinting at activity. Yet at ground level, Mars is eerily still. A thin whisper of carbon dioxide atmosphere, less than 1% the density of Earth's, barely stirs the fine sand. It is a world that seems to be holding its breath in endless quiet. Once, billions of years in the past, Mars was more Earth-like. Ample evidence tells us that long ago, Mars had liquid water on its surface. Ancient river valleys, delta formations, and lake beds are etched into its terrain. Rovers and orbiters have found minerals that form in water, clay in craters that were once lakes, and signs that a vast ocean might have covered the Martian northern lowlands. Back then, Mars likely had a thicker atmosphere and a warmer climate that could sustain liquid water. But those days are long gone. Over time, the planet's core cooled and its magnetic field faded. The solar wind stripped much of the Martian atmosphere into space. The surface water either froze beneath the soil or escaped. Now, under a salmon-pink sky, the rivers and lakes have vanished. Mars's once flowing waters are locked away as ice in the polar caps and permafrost, or lost to space entirely. Today, Mars is a freeze-dried world. Daytime near the equator in summer might feel almost mild under the bright sun, reaching perhaps 20 degrees, 68 degrees. But as soon as the sun sets, the heat radiates away into space, and temperatures plunge far below freezing by nightfall. On a Martian winter night, it can drop to 100 degrees, 148 degrees, or lower. The thin air provides almost no insulation, no moderation of temperature, and no protection from the sun's ultraviolet radiation or cosmic rays. Any liquid water exposed on Mars would either quickly boil away in the low pressure or freeze solid. To stand on Mars, an astronaut would need a pressurized suit and life support. There is essentially no breathable oxygen. The sky often has a butterscotch hue during the day, tinted by fine dust suspended in the air, and a hazy reddish or blue-grey at sunset. It's an alien sky, dimmer than Earth's, with a sun about 2/3 the size it appears from our perspective. Yet Mars is not without wonders. Towering above the flat deserts is Olympus Mons, the largest volcano in the solar system. A mountain about 22 kilometers high, 3 times taller than Everest, and so wide at its base that an observer on its slope wouldn't even see the mountain's peak, as the curvature would hide it. Along Mars's equator runs Valles Marineris, a colossal canyon system that stretches for 4,000 kilometers, as wide as North America, and dives up to 7 kilometers deep. If placed on Earth, Valles Marineris would span the entire United States and then some. These features hint at a once active Mars, with hot flowing magma and shifting crust that created giant volcanoes and rifts. Those processes have gone mostly silent. Olympus Mons appears to be an ancient volcano now long dormant. Mars still has weather, albeit a very thin version. Wispy clouds of ice crystals sometimes float high in the atmosphere, and at dawn or dusk they can create delicate blue-white streaks across the sky. Wind on Mars, though feeble, can pick up the fine dust and occasionally whip it into dust devils, short-lived whirlwinds that dance across the plains, leaving dark tracks. On rare occasions, the winds raise massive dust storms that can engulf the entire planet, turning the atmosphere opaque orange for weeks. When the dust settles, a ghostly pale sun emerges again to shine down on a landscape strewn with rocks and boulders under a sky that has regained its clarity. At the poles in winter, carbon dioxide from the atmosphere freezes out into slabs of dry ice, adding a seasonal cap atop the permanent water ice caps. In spring, this CO2 sublimates back into gas, sometimes in sudden jets that burst through the thawing ice, eroding the surface in strange patterns. Mars breathes in this way, thin breaths of gas moving in and out of storage at the poles with the seasons. In the dull pink sky of Mars, two tiny moons make their rounds. Phobos and Deimos, whose names mean fear and panic, are little more than captured asteroids, each just a few tens of kilometers across. They are irregular in shape, lumpy, and cratered like potatoes. Phobos, the larger and closer moon, orbits Mars so rapidly, about once every 8 hours, that it rises in the west and sets in the east, completing 2 orbits each Martian day. It hangs relatively large in Mars's sky, though still appearing only perhaps a third the apparent width of our moon from Earth, and would be seen racing across every few hours. Deimos, smaller and farther out, takes roughly 30 hours to circle Mars and appears more like a slow-moving star in the sky. These moons may one day break apart or crash into Mars. Phobos is inching inward over the eons, but for now, they are silent companions, likely wayward rocks snared by Mars's gravity long ago. If you stood on Mars, you'd occasionally see Phobos pass overhead, zipping by almost imperceptibly, while Deimos would look like a bright star taking a long path above the horizon. Mars has long fueled human imagination. In the late 19th century, some astronomers observing Mars under early telescopes thought they saw straight lines on its surface, canals that they speculated might be engineered by intelligent beings. This idea captured the public fancy, inspiring tales of Martians and alien civilizations. We now know those linear features were illusions of optics and imagination. Spacecraft and rovers have revealed no cities or canals, only craters, rocks, and dust. So far, Mars appears barren. No trace of life has yet been found on its surface, not even a single microbe. But the question remains tantalizing. Did life ever spark on Mars when it was warm and wet? And might some remnants persist underground? The soil analysis by robotic landers has hinted at complex chemistry. Meteorites from Mars found on Earth have stirred debate by containing structures that some thought could be fossils, though most evidence suggests non-biological origins. The search continues, and Mars keeps its secrets a little longer. Mars stands as a lonely outpost of the Sun, a world that had the ingredients for life's dawn, but then fell into dormancy. In its solitude, Mars reminds us of both the frailty and resilience of planets. It shows how a once promising world can change, losing its air and water, yet also how features like towering volcanoes and grand canyons can remain, preserved in the absence of flowing water or shifting plates. The red planet's story of change and loss calls out across the void, capturing our curiosity and beckoning us to uncover its mysteries. Perhaps one day, in the not-too-distant future, humans will answer that call. The first footsteps might press into Mars's dusty soil, and explorers could stand beneath its butterscotch sky, finally turning pages of the Martian story that have lain unread for eons. For now, Mars remains a quiet enigma, an ancient, silent world that keeps watch from afar, waiting for us to continue the journey. Moving onward beyond Mars, the nature of the solar system shifts dramatically. At the edge of Mars's realm lies a vast gulf filled with countless small rocks and icy fragments. The asteroid belt, a band of debris encircling the Sun. These are the leftover building blocks that never coalesced into a planet, due in part to the disruptive gravity of Jupiter beyond. In this sparse, rocky ring, pieces of primordial planets circle quietly, some only pebbles, others hundreds of kilometers wide like Ceres, the belt's dwarf planet queen. Crossing this silent terrain of asteroids marks the boundary between the inner, rocky worlds and the outer, giant planets. As we pass through the asteroid belt's domain of darkness and ancient stones, we prepare to meet the giants that rule the outer solar system, Jupiter and Saturn. We arrive at Jupiter, the king of planets. Jupiter is a behemoth, more than 11 times the diameter of Earth and over 2.5 times more massive than all the other planets combined. This giant could contain over 1/300 Earths inside it if it were hollow. It is composed mostly of hydrogen and helium gas and has no solid surface in the traditional sense. As we approach, we see its upper atmosphere adorned with bands of pale yellow, ochre, and white. These bands are cloud layers stretched into stripes by Jupiter's rapid rotation. One day on Jupiter lasts only about 10 hours. Amid the bands, an enormous storm swirls near the planet's equator. The Great Red Spot, a vast oval of brick red hues. This raging storm has been churning for centuries, at least since telescopes observed it in the 1600s. And it is so large that 2 or 3 Earths could fit side by side within it. From afar, however, even this great cyclone is just one feature on Jupiter's immense banded sphere. Jupiter is alive with motion. Its cloud bands slide past each other in opposite directions, driven by winds that reach hundreds of kilometers per hour. Lighter-colored zones and darker belts wrap around the planet, the result of convection and high-speed jet streams in Jupiter's skies. Towers of cloud can erupt like thunderheads in the turbulent atmosphere, and bright bolts of lightning have been recorded flashing deep within those clouds. Some of the most powerful lightning in the solar system. The planet emits more heat from its deep interior than it receives from the distant sun. This internal heat, left from its formation and generated by slow gravitational compression, powers weather patterns unlike any on Earth. Beneath the upper clouds, as one descends, the gases grow denser and hotter, transitioning into a supercritical fluid state. Hydrogen, under crushing pressures, gradually becomes a hot, dense liquid, and eventually an exotic form of matter called liquid metallic hydrogen, which conducts electricity. Jupiter likely has a dense core of heavier elements about 20,000 kilometers across, but it is buried under tens of thousands of kilometers of fluid molecular and metallic hydrogen, forever hidden from direct view. Unseen by human eyes, but immensely important, Jupiter also possesses an enormous magnetic field, far stronger than Earth's. This magnetic field traps charged particles in intense radiation belts around the planet and funnels particles toward Jupiter's poles to create brilliant auroras. At Jupiter's north and south poles, ultraviolet auroral lights ring the dark polar skies, far more powerful than Earth's northern lights. Jupiter's magnetosphere, its magnetic influence, extends millions of kilometers into space, forming the largest protective bubble in the solar system. In fact, if we could see it, Jupiter's magnetosphere would appear several times larger than the full moon in our sky. It even stretches beyond the orbit of Saturn at times, showcasing the king planet's invisible yet formidable presence. Circling this giant is an entourage of moons, a whole miniature solar system of diverse worlds. Over 90 known moons orbit Jupiter, ranging from small captured asteroids only a few kilometers wide to enormous moons the size of planets. The 4 largest, known as the Galilean moons, after Galileo, who spotted them in 1610, are particularly remarkable and varied. Io, the innermost of the four, is a tortured, volcanic world. Tremendous tidal forces from Jupiter's gravity, a pull constantly squeezing and flexing Io as it orbits, heat its interior and fuel hundreds of active volcanoes on its surface. Sulfur and sulfur dioxide frost paint Io in surreal shades of yellow, orange, and white. It is the most volcanically active body in the solar system. Some volcanoes erupt lava fountains dozens of kilometers high, and vast lakes of molten sulfur dot its landscapes. The entire moon is effectively turning itself inside out over time, continuously repaved by fresh lava. Just next door, Europa wears a smooth shell of bright ice. Its surface is crisscrossed by long, dark streaks and cracks, but very few craters, an indication that the surface has been renewed relatively recently. Beneath Europa's icy crust lies a global ocean of liquid water, kept unfrozen by heat from tidal flexing, similar to Io's, but less intense. This hidden ocean, insulated under kilometers of ice, could be 100 kilometers deep and contains more water than all of Earth's oceans combined. In the darkness of that European sea, warmed by the moon's interior, could conditions exist for life? Europa tantalizes us with that possibility. Occasionally, plumes of water vapor have been observed venting from its surface cracks, hinting at activity below. Europa's smooth, bluish-white exterior, laced with reddish-brown mineral stains along fractures, makes it one of the most intriguing objects in the solar system, a potential cradle for life in an otherwise forbidding environment. Ganymede, the third Galilean moon, is the largest moon in the solar system, bigger in diameter than the planet Mercury. It's a mixture of rock and ice, and is the only moon known to have its own internally generated magnetic field. Ganymede's surface is a contrast of two terrains: dark, ancient, crater-saturated regions, and somewhat lighter, younger regions, marked with an extensive network of grooves and ridges, as if the ice crust was stretched and refrozen. This suggests Ganymede may have had tectonic activity in the past, and possibly even a subsurface ocean as well. Ganymede orbits a bit farther from Jupiter, beyond the fiercest of Jupiter's radiation belts, and it presents a more benign face, half in deep freeze, half geologically restless. Callisto, the fourth Galilean moon, lies even farther out. It is a heavily cratered, ice rock world that appears to have been long dead geologically. Its entire surface is ancient, densely pockmarked by impacts, making Callisto a record keeper of the early solar system. Unlike Io or Europa, Callisto shows no signs of internal activity or tidal heating. It's far enough from Jupiter that it doesn't experience the strong tidal flexing. Instead, Callisto is like a preserved relic. It's often considered the most heavily cratered object we know. The bright splashes of ejected ice around its craters, and a giant series of concentric rings from a massive impact, the Valhalla Basin, are its defining features. Callisto's inert surface and interior might nonetheless hide a surprise. A subsurface ocean has been hypothesized there too, at great depth, suggesting that even quiet Callisto could harbor a hidden layer of liquid water. These four moons alone display astonishing variety: fire and sulfur on Io, ice and ocean on Europa, a magnetic field and grooved ice on Ganymede, and a cratered antique face on Callisto. They are like a miniature planetary system, each with its own history and character, and they are only the largest of Jupiter's retinue. Dozens of smaller moons dance around Jupiter as well, Some trail ahead of and behind Jupiter in its orbit, captured asteroids caught long ago. Others orbit closer in, small potato-shaped rocks that may have been born from collisions. Jupiter even sports a thin, dusty ring of its own, discovered by Voyager spacecraft. Nothing like Saturn's bright rings, but a faint girdle of particles, likely shed from its innermost moons. In all, the Jovian system is a cosmic archipelago of worlds, large and small, circling the immense gravity well of Jupiter. Not to be outdone, Saturn comes next, orbiting farther out in the cold darkness. Only slightly smaller than Jupiter, Saturn is still colossal, about 9 times Earth's diameter and over 95 times Earth's mass. Yet Saturn is also strikingly light for its size. It's the least dense of all the planets. If there were an ocean big enough, Saturn would float in it, being less dense than water. Saturn's appearance is sublime. It wears a diffuse golden hue, with bands of cream and butterscotch-coloured clouds that are less vivid than Jupiter's, but present if you look closely. But of course, the most stunning feature of Saturn is the system of rings that encircles it. Even a small telescope reveals the planet's signature adornment. Wide, flat rings of shimmering brightness, making Saturn appear like a celestial jewel placed in a slender dish. Saturn's rings are broad, but wafer-thin, made up of countless icy particles orbiting in a flat plane around the planet's equator. From end to end, the main rings span about 270,000 kilometers, nearly the distance from Earth to the Moon. But they might be only tens of meters thick in places, essentially two-dimensional on the scale of a planet. The ring particles range in size from tiny grains of ice to boulders as big as houses. Up close, the rings would look like a vast, glittering snowstorm of ice chunks, each independently circling Saturn. They reflect sunlight like a million little mirrors, which is why we see the rings so clearly from Earth. Gaps and divisions cut through the rings, the most famous being the Cassini division, which separates the broad A and B rings. These gaps are sculpted by the gravitational influence of Saturn's moons. Some small moons, called shepherd moons, actually orbit within or just beyond the rings, their gravity herding ring particles into sharp edges and distinct bands. How Saturn's rings formed remains a topic of debate. They might be the remnants of a moon or comet that strayed too close and was torn apart by tidal forces eons ago, or leftover material from Saturn's formation that never coalesced into a moon. Whatever their origin, the rings are relatively young by cosmic standards, perhaps only 100 million years old, and may not last forever. Gradually, ring particles are spiraling down into Saturn or clumping into new moonlets. But for now, they grace the planet like a magnificent, gleaming halo frozen in space. Beneath its rings, Saturn's atmosphere is banded and dynamic, though the colours are more subdued than Jupiter's. Saturn has its own pattern of alternating belts and zones, and storms do arise. Approximately every 30 Earth years, an enormous storm erupts in Saturn's atmosphere, a great white spot, a complex of thunderstorms so large it becomes visible even in smaller telescopes as a white scar wrapping around the planet. And at Saturn's North Pole, a truly bizarre atmospheric phenomenon exists, a hexagon-shaped jet stream. This persistent six-sided pattern in the cloud tops, first observed by the Voyager spacecraft and later seen in detail by the Cassini probe, is a geometric weather pattern unlike anything seen elsewhere. Each side of the hexagon could span the distance from New York to London, and yet it remains nearly stable, rotating like a giant honeycomb. It's a testament to the complex fluid dynamics at play in Saturn's atmosphere. The hexagon even holds a rotating storm at its center, a kind of polar hurricane. It's a reminder that even in the elegance of Saturn's appearance, strange and wonderful phenomena lie hidden in the cloud tops. Like Jupiter, Saturn hosts a rich collection of moons, More than 80 are known so far, and tiny new ones are still being discovered as our instruments improve. The largest by far is Titan, an extraordinary moon that rivals some planets in size. Titan is larger than the planet Mercury, and it's the second largest moon in the solar system, after Jupiter's Ganymede. What makes Titan truly special is its dense atmosphere. Titan is shrouded in a thick orange-brown haze of organic smog that is even denser than Earth's atmosphere. Standing on Titan's surface, with the proper protection of course, you would experience a pressure about 1.5 times that of Earth's sea level. Titan's air presses down slightly more than our own. For a long time, Titan's opaque atmosphere hid its surface completely, sparking imaginations that perhaps oceans, or even life, might lurk beneath. Titan's atmosphere, rich in nitrogen like Earth's, also contains methane and ethane. In Titan's frigid environment, around 180 degrees on the surface, methane plays a role similar to water on Earth. It can condense, form clouds, and fall as rain. In fact, Titan is the only world besides Earth known to have stable liquids on its surface. Only on Titan, the liquid is not water, but hydrocarbons, like methane and ethane. Indeed, Titan's surface, as revealed by radar mapping and the Huygens lander probe, has dark, smooth lakes and seas of liquid methane and ethane in its polar regions. There are river channels carved into the icy ground, likely by flowing liquid methane during Titan's mild rainstorms. Vast dune fields of dark hydrocarbon sand stretch across its equatorial regions, sculpted by gentle winds. And there may be cryovolcanoes, ice volcanoes, that ooze slushy mixtures of water and ammonia from Titan's interior, releasing methane into the atmosphere. It is an alien, yet oddly familiar world, Earth-like in its geography, with river valleys, lakes, and weather, but utterly different in its materials and temperature. It's as if we see a frozen mirror of a much earlier Earth, preserved in deep cold. If one could walk on Titan, the experience would be surreal. The dim sunlight filtered through the haze would give the sky an orange-grey colour, and daylight would feel like dusk on Earth. You might see Saturn as well, a pale golden orb looming in Titan's sky if the clouds parted, though often the smog is too thick for a clear view. The gravity is low, about 1/7 of Earth's, and with the dense air you could almost imagine strapping on wings and flying through the thick atmosphere with enough effort. The landscape under your feet would be solid water ice as hard as rock, strewn with hydrocarbon-rich sands and puddled with pools of liquid methane. It would be cold beyond anything on Earth, yet strangely Earth-like in appearance. Titan feels like a world with its own active cycles, a methane cycle analogous to Earth's water cycle, and it stirs curiosity about whether some form of simple life could exist in its lakes or soil, using liquid methane instead of water. Another of Saturn's jewels is the tiny moon Enceladus. Bright white and only about 500 kilometers across, Enceladus is covered in fresh, clean ice that makes it one of the most reflective objects in the solar system. It shines like a little white snowball against the darkness of space. The surface of Enceladus looks young and relatively free of craters in many areas, crisscrossed by cracks and smooth plains of ice, suggesting it has been resurfaced over time. But Enceladus is more than just an inert ice ball. It is active. At Enceladus's south pole, long fractures in the ice, nicknamed tiger stripes for their appearance, continuously erupt with geysers of water vapor mixed with ice crystals and organic compounds. These plumes shoot into space hundreds of kilometers high, feeding a faint ring of fine ice particles that orbit Saturn, the E-ring. The source of these geysers is a subsurface ocean of liquid water beneath Enceladus's icy crust. Tidal flexing by Saturn's gravity likely provides the heat to keep this hidden ocean from freezing solid. Where there is liquid water, heat, and organic molecules, the three ingredients for life as we know it are present. Enceladus, tiny and seemingly insignificant, thus became one of the most exciting places in the search for extraterrestrial life. NASA's Cassini spacecraft flew through the geyser plumes and detected complex organics, hinting at hydrothermal activity on an ocean floor inside Enceladus. It's as if this little moon has a warm, wet heart in an unlikely place. In the South Polar region, one could imagine standing on the fissured ice plains and seeing geysers of fine, misty spray silhouetted against the starry sky, lit by a distant sun. A breathtaking sight and a promise of geological vitality. Saturn's other moons each have their own characters. Icy Rhea, Saturn's second largest moon, is cratered and cold, an airless body quietly orbiting for billions of years. Iapetus, another large moon, is one of the strangest. One hemisphere of Iapetus is as bright as snow, while the other is as dark as coal. This stark two-tone coloration makes Iapetus look like a yin-yang symbol in space. It also has a tall ridge running along much of its equator, giving it a walnut-like appearance. Dione and Tethys, mid-sized moons, have cracked surfaces hinting at past geologic activity. Enceladus we've met in detail. There's also Mimas, a smaller moon with a giant crater that makes it resemble the Death Star from fiction. Hyperion is an irregularly shaped moon that tumbles chaotically, its surface covered in deep, sponge-like craters. Titan, Enceladus, Iapetus, Rhea, and all these moons, big and small, along with Saturn's majestic rings, form a magnificent system, a celestial ballet orchestrated by gravity. Each moon adds its note to Saturn's symphony, and each one could warrant its own story. Together, they affirm that the outer solar system harbours incredible diversity and wonders. Jupiter and Saturn, our solar system's gas giants, dominate the outer realms with their sheer size and complex systems of rings and moons. These colossal planets do more than impress with beauty, however. They also act as guardians of the solar system. Their powerful gravities have shepherded and influenced countless smaller bodies over the ages. Jupiter, in particular, serves as a cosmic shield for the inner planets. Its immense gravitational pull can draw in or deflect wayward comets and asteroids that wander into the inner solar system. Many comets that might have plunged toward the inner planets over millions of years have instead been captured or flung away by Jupiter's gravitational slingshot. By picking off some of these potential threats, Jupiter has likely reduced the number of catastrophic impacts on Earth and its neighbours. In the formative years of the solar system, the migrations and gravitational tugs of Jupiter and Saturn helped shape the final layout of the planets. Their movements may have scattered some would-be planets or planetesimals, clearing gaps, as Jupiter did with the asteroid belt, preventing a planet from forming there. Some theories suggest that an early inward and then outward migration of Jupiter and Saturn stirred up the asteroid and comet belts, causing a late rain of impacts on the inner planets that may have delivered water. And later, as they moved apart, creating a relatively stable configuration that has lasted to this day. Without Jupiter's massive presence, Earth might have been struck far more often by large comets, possibly resetting the evolutionary clock repeatedly. Thus, in a very real sense, these giant planets have protected and influenced the trajectory of life on Earth by reducing the number of devastating cosmic collisions. They are our gravitational guardians, as much as they are our distant giants. As we drift past Saturn, we leave behind the bright realm of the gas giants. The sunshine here has grown weaker. The warmth from the sun is faint and tinged with the deep cold of space. Beyond Saturn's orbit, we approach the domain of the ice giants, Uranus and Neptune, the outermost planets circling the sun. Here we stand at the threshold of the solar system's final frontier, where even larger mysteries and more distant worlds await. Uranus comes into view next, the seventh planet from the sun, rolling along in the dim twilight of the distant solar system. This pale blue-green world is often called an ice giant. It's smaller than Jupiter and Saturn, but still about 4 times the diameter of Earth, big enough to contain 64 Earths by volume. Uranus holds a unique distinction among planets. It spins on its side. Its axis is tilted by about 98 degrees, meaning it rotates almost lying over on the plane of its orbit. At some point in the distant past, a titanic collision, or a series of impacts, may have knocked Uranus over, leaving it rolling around the sun like a tilted barrel. As a result, for part of Uranus's 84-year orbit, one pole points almost directly at the sun, while the other is plunged into long darkness, leading to extreme seasons unlike any other planet experiences. Imagine a summer where the sun never sets for 21 years at the North Pole, while the South Pole is in a 21-year winter night. Then, as Uranus moves to the opposite side of its orbit, the situation reverses. Such is the bizarre seasonal cycle of Uranus. In the Uranian sky, the sun is a small, distant lamp, only about 1/400th as bright as it is at Earth. Just a very intense star, albeit enough to cast faint shadows. This planet was unknown to the ancients. It was first discovered in 1781 by William Herschel's telescope, expanding the known boundaries of the solar system for the first time in modern history. The atmosphere of Uranus is a cold mix of hydrogen, helium, and a trace of methane. The methane is what gives Uranus its gentle cyan or sea green tint, as methane gas absorbs red wavelengths of sunlight and reflects the blue-green. For a long time, Uranus appeared nearly featureless, a bland, softly coloured sphere, leading astronomers to think it had a very placid atmosphere. But later observations and the Voyager 2 flyby in 1986 showed subtle bands and occasional storm features, especially when viewed in infrared light. Uranus's weather is indeed more muted than Jupiter's or Saturn's, but it's there. High-altitude haze, faint cloud bands, and at times great storm systems that can erupt and then subside. One reason features are hard to see is because Uranus has a layer of haze in the upper atmosphere that smears out details. Still, at least one dark storm and several white cloud tops, likely methane ice clouds, have been observed by large telescopes in recent years, indicating Uranus is not completely asleep. Uranus is also encircled by a set of thin, dark rings. These rings, discovered in 1977, when Uranus passed in front of a star and the star's light blinked on and off, intercepted by rings, are much fainter and narrower than Saturn's. Composed of dark, carbon-rich particles, the Uranian rings are difficult to see directly. They reflect very little sunlight. They form narrow bands, and one of them, the Epsilon ring, is the brightest and was the first discovered. These rings are likely debris from shattered moons or leftover material shepherded by tiny moons embedded within them. They stand almost vertically relative to the Sun now, aligned with Uranus's sideways orientation, and from Uranus's perspective, they would circle around its equator, edge on, as seen from the Sun. Uranus is accompanied by a retinue of moons. At least 27 are known. Most of these moons are icy bodies, darkened by dust, many just tens of kilometers across. They have poetic names taken from literature, mostly Shakespearean characters like Titania, Oberon, Ariel, Miranda, and so on, rather than the classical mythological names of most other planetary moons. The largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, range from about 500 to 1,500 kilometers in diameter. They present varied surfaces. Some are covered in old craters and dark material, while others show signs of past geological activity, like canyons or strange surface patterns. Titania and Oberon, the two largest, sit at the far edges of the Uranian system, half ice and half rock, their surfaces marked by impact basins and long faults where the crust cracked as they cooled. Ariel and Umbriel, mid-sized moons, show patches of young surface and dark ancient regions, respectively. One moon, Miranda, stands out as especially bizarre. Miranda is the smallest of the major moons, about 500 kilometers across, yet its surface looks as if it was shattered and haphazardly put back together. It has enormous canyons, one with cliffs estimated at 20 kilometers high, alongside regions of ridges and troughs, and other areas that are relatively smooth. It's a geological patchwork, possibly the result of a past collision or tidal heating episodes that caused partial melting and refreezing. If one could stand on Miranda near the foot of Verona Rupes, the tallest known cliff in the solar system, the cliff would tower up into the black sky, its top vanishing into the horizon curve. Such a landscape is mind-boggling in scale for so small a moon. All these moons, along with the rings, orbit in the same tilted plane as Uranus's equator. So Uranus and its system essentially spin like a wheel around the Sun. This tipped configuration makes Uranus's system unique, a sort of cosmic sideways carousel, giving astronomers much to ponder about how it came to be. Beyond Uranus lies Neptune, the eighth and outermost known planet of our solar system. Neptune is a world of deep, rich blue, often appearing as a vivid cobalt or azure dot in photographs. It was the first planet discovered not by direct observation, but by prediction. Mathematicians in the mid-19th century noticed Uranus was straying from its expected orbit and inferred that a further planet's gravity was tugging on it. In 1846, telescopes pointed to the predicted spot in the sky, and there was Neptune, almost exactly where the calculations suggested, a triumph of human reason. Neptune is similar in size to Uranus, with a diameter about 3.9 times that of Earth, and it's another ice giant, meaning a significant portion of its bulk is made of water, ammonia, and methane ices, in fluid forms deep in the planet, along with hydrogen and helium gas. But Neptune distinguishes itself with a more dynamic atmosphere, despite receiving even less solar energy than Uranus. Neptune's atmosphere, like Uranus's, is mostly hydrogen and helium with a touch of methane. But Neptune's hue is a more striking blue, possibly due to trace amounts of other gases or atmospheric particles that further tint its appearance. The weather on Neptune is surprisingly lively. Winds are the fastest known in the solar system, measured at over 2,000 km/s, 1,200 miles, near the equator. These roaring winds drive Neptune's cloud bands and storms. When Voyager 2 flew by Neptune in 1989, it spotted what was dubbed the Great Dark Spot, an Earth-sized storm system in Neptune's southern hemisphere, somewhat akin to Jupiter's red spot. This storm had very fast winds encircling it, and bright white clouds of methane ice fluttering around its edges. These companion clouds form as gases are uplifted over the storm, similar to lenticular clouds crowning a mountain peak on Earth. Intriguingly, by the mid-1990s, the Great Dark Spot had vanished. Neptune's storms seemed to be more short-lived, coming and going over years or decades. Hubble Space Telescope and later observations have since seen other dark spots appear and dissipate in Neptune's atmosphere, showing that the weather is ever-changing. Apart from dark vortices, Neptune also exhibits bright methane cloud features, some forming bands or cirrus-like stretches at high altitude. One famous feature is Scooter, a fast-moving white cloud group that Voyager tracked zipping around Neptune. The powerful winds and storm systems on Neptune likely draw their energy from the planet's internal heat. Neptune, like Jupiter and Saturn, radiates more heat than it gets from the Sun. Despite being so far from the Sun, Neptune is not a static, frozen ball. It's a planet where physics and chemistry still dance vigorously in the frigid twilight of space. Neptune, like its sibling, also wears a collection of rings, though they are faint and not symmetrical. Neptune's rings are thin, dusty, and clumpy. They are composed of extremely dark material, possibly organic rich dust or radiation-darkened ice. Unusually, Neptune's rings form distinct arcs in some segments. When Voyager 2 approached, it saw bright patches in the rings, concentrations of material. It's thought that gravitational interactions with Neptune's moons confine some of the ring particles into those arcs, rather than letting them spread evenly into a full ring. These arcs have poetic names like liberty, equality, and fraternity. While much sparser and darker than Saturn's magnificent rings, Neptune's rings add a subtle adornment to the planet, barely visible except to our best cameras. And Neptune too has moons. 14 are known so far. By far the largest is Triton, a moon almost as large as Earth's moon, about 2,700 kilometers across. Triton is a world that would stand out anywhere, but it orbits Neptune, making it a gem of the outer solar system. Uniquely, Triton orbits Neptune in a retrograde direction, meaning it goes around opposite to Neptune's rotation. This suggests Triton is not an original moon of Neptune, but a captured object, likely once a dwarf planet from the Kuiper belt that strayed too close and was ensnared by Neptune's gravity. Having been captured, Triton's orbit would have been highly eccentric at first, and over time, tidal interactions made it circular and also caused Triton to gradually spiral inward toward Neptune, very slowly. Eventually, billions of years from now, Triton may come so close that Neptune's gravity will tear it apart, potentially creating a spectacular ring. But for now, Triton remains intact and is one of the coldest active worlds we've seen. Triton is bitterly cold, with a surface temperature around 235 degrees, 391 degrees. The sunlight at Neptune's distance is feeble. The sun is just a tiny bright star from Triton's surface. Yet despite this deep freeze, Voyager 2 discovered that Triton is not a dead world. Its surface, composed of frozen nitrogen, water ice, and dry ice, CO2, shows relatively smooth plains and strange melon skin textures in places, indicating resurfacing. Voyager observed what at first looked like clouds, but turned out to be something astonishing: geysers. Dark, wind-blown plumes were seen rising about 8 kilometers high from Triton's surface and drifting downwind for hundreds of kilometers. These are nitrogen gas geysers, likely caused when subsurface sunlight, even if weak, warms a translucent layer of frozen nitrogen, enough to vaporize some of it from below, building pressure and then erupting through cracks in the crust, carrying dark particles, possibly carbon-rich compounds, with it. Triton has a very thin atmosphere, mostly nitrogen, with a trace of methane, and it's thick enough to have hazes and to spread the geyser plumes into veils. The atmospheric pressure is 1/70,000th of Earth's, virtually a vacuum, but enough to detect. Triton's surface has a pinkish tint in some areas, from tholins, organic compounds created by sunlight on methane, and a curiously mottled cantaloupe terrain elsewhere, covered in pits likely formed by ground collapse or ice upwellings. There are relatively few impact craters, which implies the surface has been modified in the relatively recent past, geologically speaking. As Neptune's largest moon, and one with active geology, Triton stands out as a captured wanderer that became one of the most intriguing moons in the solar system. If you could stand on Triton's pale pink plains, you might see a faint sun in a dim sky, a low horizon wrapped in a thin haze, and in the far distance, perhaps a streak of a nitrogen geyser catching the sunlight, a silent fountain on a frozen world. Above, Neptune would loom large, about the size of a tennis ball held at arm's length, blue-green and banded, a majestic backdrop in Triton's sky. Neptune marks the last stop among the planets, but it is not truly the end of the solar system. Far beyond Neptune's orbit, the Sun's influence persists in other forms, and a new population of worlds dominates the darkness. Here lies the Kuiper Belt, a broad realm of icy bodies encircling the Sun, remnants from the solar system's formation that never gathered into a single planet. This is a distant mirror of the asteroid belt, but colder and more diffuse, stretching from just beyond Neptune, around 30 AU from the Sun, to perhaps 50 AU or more. Pluto is the most famous of these distant worlds. Once considered the ninth planet, Pluto is now classified as one of the largest known Kuiper Belt objects and a dwarf planet. It dwells, on average, about 5.9 billion kilometers, 3.67 billion miles, from the Sun, roughly 40 times farther out than Earth. At that distance, a single orbit takes about 248 Earth years to complete. Sunlight is so attenuated that at noon on Pluto, the illumination is only as bright as early twilight on Earth. The Sun, though still the brightest object in Pluto's sky, would appear only about 1/30th the width it appears from Earth, a fiercely bright point star rather than a big warming disk. The feeble daylight creates dim, greyish-blue scenes on Pluto's surface, as seen by the New Horizons spacecraft during its flyby. Pluto is a small world of rock and ice, about 2,377 kilometers in diameter, roughly two-thirds the size of Earth's moon. Discovered in 1930 by Clyde Tombaugh, it remained a tiny, blurry speck in telescopes for decades, its features a mystery. But in 2015, when NASA's New Horizons spacecraft flew past Pluto, we finally saw this little world up close, and it stunned us with its complexity and beauty. We saw a large, bright, heart-shaped feature dominating one side of Pluto. This heart was informally named Tombaugh Regio, after Pluto's discoverer. One lobe of the heart, called Sputnik Planitia, is a vast plain of nitrogen ice, as smooth as a sheet of freshly poured wax. It's a young surface, essentially no craters, indicating it has been renewed or reshaped in the last few million years at most. The nitrogen ice here convects slowly like a boiling pot, albeit on a timescale of tens of thousands of years per cycle, erasing old features. Polygonal cells of convection, each perhaps 30-50 kilometers across, have been mapped out, showing where warmer nitrogen ice rises and cooler ice sinks. It's a process similar to what happens in Earth's mantle with rock, but here with soft, cold nitrogen ice. At the margins of Sputnik Planitia, the ice has forced itself into rugged mountains of water ice, shoving aside older terrain. Elsewhere on Pluto, we found water ice mountains, standing up to 3 to 4 kilometers tall. Jagged, blocky peaks that might be the exposed bedrock of Pluto, since at Pluto's cryogenic temperatures, Water ice is hard like stone. Some mountains appear to be solitary monoliths, while others form ranges like the Al-Idrisi Montes on the northwestern edge of Sputnik Planitia. Between the mountains lie patches of dark plains covered in tholin, dark red organic gunk created by solar ultraviolet light interacting with methane in Pluto's air. We also saw enormous pits and possible ice volcano calderas. One large feature, Right Mons, looks like a potential cryovolcano. A broad mound with a depression at the top, which may have once oozed a slurry of water ammonia ice instead of lava. Pluto's surface colors range from charcoal black to brilliant white. The whites are mainly fresh ices, nitrogen, methane, and carbon monoxide frost that reflect sunlight well. The darkest areas, like a region called Cthulhu Macula that spans much of Pluto's equator, are covered in those red-brown tholin deposits and are heavily cratered, indicating old terrain. Between these extremes are shades of ochre and orange. Faint, layered hazes in Pluto's extremely thin atmosphere catch the sunlight and produce a blue scattering glow, much like the blue hazes seen in sunsets on Earth or smoggy cities. New Horizons photographed Pluto's atmosphere, backlit by the sun, and revealed up to 20 distinct layers of haze extending over 200 kilometers high. That was astonishing for such a small planet with weak gravity. Pluto has an atmosphere, though tenuous, mostly nitrogen like Earth's, with a touch of methane and other gases. At Pluto's surface, the atmospheric pressure is about 1/100,000th of Earth's, a near vacuum, but enough to carry haze particles and form frosts. During Pluto's 248-year journey around the Sun, it draws a bit closer for a couple of decades, as it did in the 1980s and 90s, even coming closer than Neptune for a time due to its elliptical orbit, and then recedes. When farther, much of its atmosphere is thought to freeze out on the surface as frost. When nearer, it sublimates back into gas. We happened to catch Pluto not long after its closest approach to the Sun. 1989 was the perihelion, so it still had a substantial atmosphere when New Horizons flew by. The surface temperature on Pluto is about 229 degrees, 380 degrees. In the sky from Pluto, the sun shines about 1,000 times dimmer than on Earth, but it's still about 250 times brighter than our full moon, enough to cast shadows and illuminate the landscape in a faint blue daylight. Standing on Pluto at noon, one could read a book, but it would feel like early evening lighting. The stars would be visible in the sky, and the Milky Way would shimmer brilliantly. In Pluto's sky, the constellations would appear almost the same as from Earth, just with a different pattern of bright stars due to being 5.5 light-hours away from us. Pluto reminds us that even at the edge of the Sun's domain, there are fascinating, dynamic places that defy our expectations of a static frozen lump. One of Pluto's most remarkable features is its relationship with its largest moon, Charon. Charon was discovered in 1978, and it's so large relative to Pluto, about half Pluto's diameter and 1/8 its mass, that Pluto and Charon are sometimes referred to as a double dwarf planet system. They are tidally locked to each other, meaning Pluto shows the same face to Charon and Charon the same face to Pluto at all times. They orbit a common center of gravity that lies outside Pluto, in the space between them. Charon orbits about 19,000 kilometers from Pluto, and the pair dance around each other every 6.4 days. For a long time, we had no clear images of Charon, but New Horizons changed that. Charon turned out to have a surprisingly complex geology as well. Its northern region is capped by a vast reddish area, unofficially called Mordor Macula, likely a deposit of tholins that originated from gases escaping Pluto and then falling onto Charon's pole. Charon's surface elsewhere is mostly water ice, much of it grey, with a large equatorial belt of canyons and troughs. A colossal canyon named Serenity Chasma stretches over 1,000 kilometers across Charon, cutting miles deep, possibly the result of Charon's interior ocean freezing and expanding, cracking the surface. The southern hemisphere appears smoother and less cratered, hinting that some process may have resurfaced it, perhaps cryovolcanism or tectonics in the past. Charon's interplay with Pluto likely caused internal heating early on, which might have melted some of its interior water ice. To an observer on Pluto's surface, Charon would loom large, never rising or setting, but hanging in the same spot of the sky, going through phases from new to full. It would appear about 7.5 times larger in Pluto's sky than our moon does to us. Conversely, from Charon, Pluto would dominate the sky, fixed in place, displaying its heart and dark patches to Charon's near side eternally. The Pluto-Charon system is a beautiful example of a binary pair, two worlds locked in a gravitational embrace. Besides Pluto and Charon, the Kuiper Belt is home to numerous other known dwarf planets and countless smaller bodies. There is Eris, nearly Pluto's twin in size, slightly smaller in diameter but slightly more massive, discovered in 2005. Eris orbits even farther out, about 96 AU at its far point, and sparked the debate that led to Pluto's reclassification. Eris has its own tiny moon, Dysnomia, and is so far that the Sun is merely a pinpoint. We haven't visited it yet up close. There's Makemake, a slightly smaller dwarf planet, and Haumea, an elongated, rapidly spinning object with a day lasting only 4 hours, which has a couple of its own moons and a surface of crystalline water ice, possibly due to resurfacing from ancient collisions. Countless smaller icy worlds, perhaps tens of thousands over 100 kilometers across, and trillions of comet-like bodies, inhabit this distant reservoir. They orbit quietly in the cold, in resonances or random distributions, some clumped by the gravity of the giant planets. Occasionally, gravitational nudges, perhaps even from an as-yet unseen distant large planet or passing stars in the Sun's neighborhood, can send one of these bodies onto a new path that takes it into the inner solar system. We then see it as a comet gracing our skies. The Kuiper Belt is like a vast, icy wilderness at the frontier of our solar system, holding clues to its birth. In recent years, astronomers have speculated about a possible Planet 9 much farther out, whose gravity might be clustering some extreme orbits, but so far it remains hypothetical. If it exists, it would lie tens of billions of kilometers away, truly on the fringe of the Sun's influence. Eventually, as we travel still farther outward, even the Kuiper Belt's population peters out. We reach a point where only the occasional small icy body might be found wandering alone. But the solar system doesn't end even there. The Sun's gravitational influence extends perhaps a quarter of the distance to the nearest stars. We enter the realm of the Oort cloud, a vast, spherical swarm of icy objects that surrounds the solar system like an enormous cometary halo. The Oort cloud is thought to begin perhaps a few thousand AU, astronomical units, from the Sun. 1 AU is the Earth-Sun distance, and extend out to 50,000 AU or more, about 0.8 light-years, and possibly in a sparse form out to 100,000 AU, 1.6 light-years. This region is so distant that the Sun's light is just a feeble glow, and the gravitational pull of other stars and the galaxy start to rival the Sun's influence on objects. Trillions of icy bodies, ancient primordial comets, are believed to inhabit the Oort cloud, slowly orbiting in all directions. They are too far to detect individually, None has been observed in place. Their existence is inferred from comet trajectories. But occasionally one falls inward. Perhaps a passing star, brushing by the solar system in its galactic orbit, gives a nudge, or the cumulative tidal forces of the Milky Way disturb an orbit. When that happens, one of these distant icy rocks begins a long plunge toward the inner solar system, accelerating under the sun's pull, eventually appearing to us as a long-period comet. These comets can have wildly tilted orbits, and some take millions of years to return, if they ever do. Some come in once and are flung out entirely, never to return. The Oort cloud is like a vast, dark nursery of comets in deep freeze, preserving materials from the dawn of our system. Imagine yourself at the edge of the Oort cloud, nearly a light year from the sun. The sun itself would be just one more star in the sky, albeit slightly brighter than those of similar type. Around you, the night sky would look much as it does from Earth. Constellations familiar, since even at this distance you're still in the sun's neighborhood relative to interstellar scales. But the environment would be unlike anything near Earth. A cold, silent expanse, with perhaps a few icy bodies faintly visible nearby. The sun's warmth almost negligible, and the pull of other stars quietly beginning to tug on you. This is the realm where the solar system yields to the interstellar medium, the thin smattering of gas and dust that fills the space between stars. One by one, humanity's spacecraft have been venturing toward these outer reaches. Among them, the most distant are Voyagers 1 and 2, twin probes launched in 1977. Over the decades, they journeyed past Jupiter and Saturn, with Voyager 2 also visiting Uranus and Neptune, sending back unprecedented close-ups of those worlds. After completing their planetary missions, the Voyagers continued coasting outward. In August 2012, Voyager 1, at about 121 AU, approximately 18 billion kilometers from the Sun, crossed the heliopause, the boundary where the Sun's continuous flow of solar wind particles gives way to the particle environment of interstellar space. Voyager 2 followed in 2018 at about 119 AU. At that boundary, the spacecraft detected a sharp drop in energetic solar particles and a rise in cosmic rays coming from the galaxy. It was the first time human-made objects had entered interstellar space. They found themselves in the vast calm between stars, having left the protective bubble, the heliosphere, that our sun creates. These voyagers carry with them golden phonograph records bearing sounds and images of Earth, our attempt to communicate something of ourselves to whoever or whatever might find them in the far future. They have continued to send faint signals back to Earth, telling us about the conditions out there, the density of charged particles, the direction of the magnetic field in local interstellar space. Now, nearly half a century since launch, they are over 23 billion kilometers from home, Voyager 1, and still going, though their power supplies wane. They will roam the galaxy long after they stop communicating, silent ambassadors from a species that once lived around a small distant star. At the edge of the heliosphere, roughly 120 times farther from the Sun than Earth is, we truly step into the cosmic sea. Beyond that invisible line, the particles that surround us no longer come predominantly from our Sun, but from other stars and cosmic events. Interstellar space is not empty. It has a thin gruel of atoms, a few cosmic dust motes, and the pervasive cosmic rays travelling through. But compared to the dense environments of planets, it is an almost perfect vacuum. Here the Sun's presence is reduced to gravity and light. It still tugs on comets in the Oort cloud, and its faint light still travels outward, eventually to other stars. Yet we are, for all intents and purposes, outside the solar system's main envelope. It is peaceful and dark. The closest star, Proxima Centauri, is still over 4 light-years away. over 30,000 times farther than the edge of the Oort cloud. The distances now become almost incomprehensible. Out here, nearly a light year from the sun, we pause and look back. The sun is now just one star among many, a particularly bright one, yes, but no longer an overwhelming source of light. It glitters like a solitary beacon surrounded by night. All the planets we visited, Mercury's sun-baked craters, Venus's shrouded inferno, Earth's vibrant blues and greens, Mars's silent sands, Jupiter's striped tumult, Saturn's ringed splendor, Uranus's tilted cyan, Neptune's windy azure, now lie far behind us, circling that tiny distant star. From this vantage, our entire solar system is a mere point of light. The grand orchestra of planets and moons is invisible, lost in the brilliance of the sun that now appears as a pinpoint. It truly sinks in how small our home is, a tiny island in a vast cosmic ocean. Drifting in the interstellar darkness, we find a profound quiet. This is the threshold between our solar system and the wider galaxy. The Milky Way's band, which our ancestors saw so clearly on dark nights, now encircles us as a highway of stars, no closer than before. But now the sun is simply one more traveller in that starry stream. In the distance ahead, that hazy band of the Milky Way is a promise of wonders yet to come. Countless stars swirled together, each a sun with its own entourage of worlds. The cosmic journey that began under ancient skies on Earth now prepares to venture into that immense sea of stars. We have voyaged from the sun's warm embrace, through the realms of all its planets, to the cold edge of its influence. At this gentle stopping point, on the verge of interstellar space, we take a moment to breathe in the star glow and reflect on the voyage so far. Beyond here lies an infinite expanse of stars and possibilities. The story of the cosmos stretches far beyond our sun, and our journey is far from over. In the silent darkness, we turn our gaze outward once more, ready to continue our voyage among the stars. The tranquil cosmos beckoning us onward. In the silent reaches beyond our solar system, we drift into the interstellar void. Here, far from any star, space feels endless and profoundly quiet. The nearest star is light years away, so distant that its light takes years to cross the darkness. This vast gulf between star systems is nearly empty, a dark ocean of thinly spread matter. On average, about 5 light years separate one star from the next, leaving immense volumes of solitude in between. Yet interstellar space is not truly empty. It is laced with an extremely diffuse haze of gas and dust, mostly hydrogen and helium, the primordial gases of the cosmos. In some regions, there may be only a fraction of an atom in a volume the size of a sugar cube. By comparison, even the best vacuum we can create on Earth is billions of times denser. Essentially, interstellar space is a near-perfect vacuum, far thinner than any atmosphere or nebula, almost devoid of substance by human standards. Drifting here, one might sense an almost supernatural calm. The temperature in this emptiness hovers just a few degrees above absolute zero, chilled by the faint afterglow of the Big Bang that permeates all of space. Tiny particles whiz through the darkness, ghostly neutrinos streaming straight through matter, and occasional cosmic rays, high-energy particles born in distant supernovae. But they are so scarce and spread out that space seems utterly still. Even light itself is rare here, aside from the dim glow of far-off stars and the pervasive, feeble whisper of the cosmic microwave background. As we float in this void between the stars, we are enveloped by darkness and serenity. The only illumination comes from distant pinpoints of starlight, so faint they barely cast a shadow. A gentle haze of starlight from the Milky Way creates a subtle background glow. If we turn back, we no longer see the comforting warmth of our sun's domain. We have left behind the protective bubble of the heliosphere, where the solar wind gives way to the interstellar medium. Now, in this lonely expanse, our journey carries us ever deeper into the cosmic night. Out here, time and distance take on new meaning. A traveller moving at incredible speed would still spend tens of thousands of years just to reach even the nearest neighbouring star. The scale of the void is humbling. Between the stars lies such vast emptiness that even Voyager 1, humanity's farthest probe, took over 35 years just to touch the threshold of interstellar space in 2012. And that is only the very outskirts of our own solar neighbourhood. Beyond that point, there is only the starry expanse stretching to infinity. Suspended in this darkness, we become aware of how gently interconnected the cosmos is. The few atoms drifting here were likely forged in stars long ago, then cast into space by ancient stellar winds, or in the final breaths of dying suns. Every grain of dust is a tiny relic, perhaps a fragment blown out from a supernova that exploded millions of years in the past. In this way, even the interstellar void carries the memory of stars. It is a silent repository of history, filled with the faint echoes of stellar lives that came before. The void also carries hints of future creation. Within this sparse medium, gravity can, over eons, gather denser clumps of gas and dust. Given time, those clumps might coalesce to form new stars. Thus, even in its emptiness, the interstellar medium is the cradle from which new suns will one day be born. This thought lends a quiet optimism to the darkness. From the scattered ashes of old stars, new light will eventually emerge. For now, however, all is tranquil and still. We drift further on, letting the vast silence wash over us. Ahead, a delicate band of light begins to come into view, a subtle brightening of the cosmic canvas. It is the collective glow of billions of distant stars. We are approaching the Milky Way, our galactic home, seen from within as a misty river of light. The great starry expanse of our galaxy beckons, softly piercing the darkness of the interstellar night. We now find ourselves gazing at our home galaxy, the Milky Way, an immense city of stars in the cosmos. From within, it appears as a hazy band of light arching across the sky on a clear night. This gentle glow is the combined light of countless distant stars, blurred together. Long before telescopes revealed its true nature, humans looked up in wonder at this milky ribbon. In Greek mythology, it was said to be milk spilled by the goddess Hera, giving rise to the name Milky Way. Other cultures imagined it as a celestial river, or the backbone of night, a shining pathway in the darkness. If we could soar high above the galactic plane, we would see the Milky Way as a magnificent spiral, like a vast pinwheel in space. Its spiral arms unwind from a bright central hub, rotating slowly over eons. Our galaxy spans about 100,000 light-years from edge to edge. Embedded in its disk are hundreds of billions of stars, along with immense clouds of gas and dust weaving between the stars. These are the raw materials from which new stars are born, and they give the spiral arms a faintly gauzy appearance. At the core of the Milky Way lies a concentrated bulge of ancient stars. This central region is densely packed, a swarm of stars orbiting a common center. And at that very centre, invisible to the eye, there resides a supermassive black hole called Sagittarius A. It contains the mass of about 4 million suns crushed into a tiny space. While this black hole itself is dark, its presence reveals itself through the orbits of stars whipping around it and occasional flares of energy as it consumes stray matter. Around the core, the stellar density is so great that night never truly falls. Stars crowd each other in a busy, radiant metropolis of light. Further out from the centre, the spiral arms spread like wide, curved highways composed of stars and nebula. Our own sun is situated in one of these unassuming spur arms, about 25,000 to 30,000 light-years away from the galactic centre. Here, in what one might call the galactic suburbs, the star population is more sparse, and space is a bit quieter. The Sun and its planets ride along with this arm as the Milky Way rotates. It takes roughly 250 million years for our solar system to complete a single orbit around the galaxy's core. The last time we were at this point in our galactic journey, dinosaurs roamed the Earth's surface, a reminder of the vast timescales at play. The Milky Way's spiral arms are not static. They are dynamic regions where stars are born and die. Thick clouds of molecular gas and dust in the arms are stellar nurseries, glowing faintly where newborn stars light them up. In these arms, we find bright young blue stars and stellar clusters that illuminate their surroundings. Between the arms are darker gaps harbouring older, cooler stars. Scattered throughout are also clusters of ancient stars, known as globular clusters, swarming in a halo around the galaxy. This halo extends above and below the disk, and even beyond the halo of stars lies an invisible halo of mysterious dark matter enveloping the Milky Way. Though we cannot see it, this dark matter's gravity helps hold our galaxy together, like an unseen scaffold supporting the spinning wheel of stars. When we look up from within this grand structure, most of the stars we see are part of the Milky Way. The soft band of light that is the Milky Way in our sky is our edge-on view of the dense galactic disk. In that glowing band, telescopes reveal myriad individual stars, clusters, and nebulae. It is a bustling panorama of cosmic activity. Yet from our perspective on Earth, it appears as a continuous, tranquil brushstroke of whitish light across the darkness. Despite its enormous scale, the Milky Way is just one galaxy among many. For a long time, humans did not realize that other galaxies existed beyond our own. The Milky Way itself was thought to be the entire universe of stars. Now we know it is one island of stars among billions of others. Still, it is our home island, and it holds a special place in our cosmic journey. As we drift through its outskirts, we appreciate the grand design of our galaxy, the spiral arms gracefully coiling, the central bulge glowing with ancient light, and our tiny star circling quietly in the galactic sea. Within the Milky Way's vastness lie all the wonders of the night sky that ancient people observed, the constellations of stars, the hazy nebulae, and the star clusters that speckle the heavens. All are part of this one enormous family of stars. It gives a comforting sense of belonging to realize that the Earth and everything we know are nestled here, in a quiet corner of this majestic galaxy. Our island of stars drifts serenely in the cosmic ocean, shining as a beacon of light and stability amid the darkness of intergalactic space. Now, as we continue our journey, we turn our attention to some of the remarkable features found within our galaxy. Scattered among the stars are vast, luminous clouds, nebulae, where the galaxy gives birth to new stars. These nebulous regions are the cosmic cradles of starlight, and they await us just ahead in our voyage. Drifting further inward along the spiral arm, we encounter one of the Milky Way's great wonders, the nebulae. A nebula is a vast cloud of gas and dust in space. In essence, a cosmic cloud floating among the stars. The term nebula simply means cloud in Latin. Some nebulae are formed by the remnants of dying stars, as we will see later. But many others are the birthplaces of new stars. These stellar nurseries are often mind-bogglingly large, spanning several light years across, yet appearing delicate and ethereal in form. Nebulae come in various forms and appearances. Some glow brightly with their own light. Hot young stars embedded within them ionize the gas and make the nebula fluoresce in beautiful colors. Others shine by reflected starlight, appearing as faint blue wisps around luminous stars. There are also dark nebulae, dense clouds of dust that block the light of stars behind them, appearing as shadowy voids in the starry background. In photographs of the sky, nebulae often display vivid pinks and reds from glowing hydrogen gas, mingled with blues and purples. Their shapes can be fantastical: wispy veils, elongated filaments, or mountain-like pillars of opacity set against the starfield. Within these tranquil clouds, a dramatic process is underway. Nebulae are rich in the raw ingredients for stars, primarily hydrogen gas, with traces of other elements and dust. Over time, gravity begins to tug on the denser regions of these clouds, causing them to contract ever so slowly. As a pocket of gas shrinks, it starts to warm up and spin, gathering more material from its surroundings. In the depths of the nebula, multiple such knots of gas can condense in tandem, each one a nascent star in the making. For tens of thousands of years, these protostars continue to accumulate mass, hidden within cocoons of dust. Eventually, when the central temperature and pressure grow high enough, nuclear fusion ignites in their cores. At that moment, a star is born. It begins to emit light and heat, pushing away the shroud of gas around it. The new stars, once they switch on, dramatically transform their parent nebula. Their intense radiation ionizes the surrounding gas, causing it to glow. Stellar winds and bursts of particles from the young stars blow cavities and channels in the cloud, sculpting it into wondrous shapes. In some nebulae, towering pillars of gas remain where denser clumps resist the eroding starlight. Within those pillars, new stars may still be forming in relative shelter. The famous Pillars of Creation in the Eagle Nebula are one such example. Monumental columns of dark cosmic dust and gas, illuminated around the edges by nearby brilliant stars. Inside those pillars, embryonic stars are nestled, slowly growing until they too emerge. One of the most studied star-forming nebulae is the Orion Nebula, visible to the unaided eye as a hazy patch in the sword of the constellation Orion. In the Orion Nebula, hundreds of young stars are in various stages of formation. Observations have even revealed that many of these newborn stars are surrounded by disks of gas and dust. These are protoplanetary disks, the beginnings of potential planetary systems. In time, some of those disks may coalesce into planets, meaning that within that nebula, not only new stars, but also new worlds are being prepared. The Orion Nebula is truly a cosmic nursery, a mere 1,350 light-years from Earth, allowing us a relatively close glimpse of star birth in action. Nebulae are often visual spectacles in astrophotography, but if one could somehow drift inside a nebula, the view would be more subtle. These clouds are extremely tenuous. A nebula that looks dense and bright in a long exposure image would appear almost transparent up close. You might see a gentle haze around you and far off concentrated glows where clusters of stars are forming. The light would be dim to human eyes as the gas's glow is spread over vast distances. Yet the environment would be rich with the ingredients of creation. All around, you'd be floating in a sea of molecules that, given millions of years, will collapse into new suns and planets. In time, a star-forming nebula disperses. The newborn star's radiation and winds eventually blow away the remaining gas, clearing out the cradle that once nurtured them. What's left might be a loose cluster of young stars shining in the void, each with perhaps its own developing planets. The remnants of the nebula may survive as faint wisps, or not at all, and the stars will drift gradually apart over millions of years. But for the duration of their formation, the nebula was their shared womb, a luminous cloud that gave rise to a new generation of stars. Not all nebulae are nurseries. Some mark stellar death instead, as when an aging star gently sheds its outer layers or a massive star explodes, painting the sky with expanding debris. The cosmos recycles its matter in this way. The gas thrown off by dying stars enriches the interstellar medium, which later forms new stars. Thus, the bright starbirth nebulae we see today may contain atoms forged in stars that died long ago. Every nebula is part of this grand cycle of stellar life and death. Having witnessed the gentle birth of stars within nebulae, we continue onward. Our journey now turns to the stars themselves, those brilliant points of light that populate the galaxy. We will explore how stars live out their lives, from their fiery youth to their final fate, in the ongoing cosmic cycle. Stars are the fundamental building blocks of galaxies, great balls of glowing plasma that generate light and heat through nuclear fusion. Every star, whether a tiny red dwarf or a massive blue giant, is born from collapsing clouds of gas and spends the majority of its life quietly fusing hydrogen into helium in its core. In this long, steady phase, called the main sequence, stars shine steadily for millions or billions of years, balanced between gravity pulling inward and the pressure from fusion pushing outward. The mass of a star governs how bright it is and how quickly it burns through its fuel. Massive stars are extremely luminous and hot, pouring out energy at a prodigious rate, while smaller stars glow more softly and economically. One remarkable aspect of stars is how their lifespans vary. A star much more massive than our Sun lives life in the fast lane. It may exhaust its fuel in only a few million years. In contrast, a small red dwarf star sips its fuel so slowly that it can shine for trillions of years, far longer than the current age of the universe. Our Sun, a medium-mass yellow dwarf, has an expected total lifetime of roughly 10 billion years. At around 4.6 billion years old, it is currently about halfway through its stable life on the main sequence. During this phase, the Sun and stars like it radiate a steady light, providing warmth and energy to any orbiting planets. Over time, however, a star's supply of core hydrogen diminishes. When a star begins to run low on its primary fuel, the delicate balance shifts. For a star like the Sun, when the core fuel is nearly spent, the core contracts under gravity, heating up as it does so. This extra heat causes the surrounding layers of hydrogen in a shell around the core to start fusing, releasing even more energy. The result is that the star's outer layers are pushed outward. The star expands to many times its original size and cools at the surface, taking on a reddish hue. It has entered the red giant phase. In this swollen state, the star's appearance changes dramatically. For instance, In about 5 billion years, our Sun will bloat into a red giant so large that it may engulf Mercury, Venus, and possibly Earth. The Sun's warm yellow light will turn into a dimmer red-orange, and its size will dominate our sky. All stars, in their later years, become some form of giant. A star around the Sun's mass expands into a red giant. A star much more massive swells even further into a red supergiant. Inside these giants, new fusion reactions begin as heavier elements are fused from helium, carbon, oxygen, and so on. But this phase is relatively short-lived. Eventually, the core can no longer sustain fusion. What happens next depends on the star's mass. For a medium-mass star like the Sun, the end is relatively gentle. Once fusion ceases in the core will collapse into a dense, hot ember, roughly the size of Earth. This exposed core is called a white dwarf, an object incredibly dense yet faint, glowing from residual heat. Meanwhile, the outer layers of the star, no longer held by the core, drift off into space. They form an expanding, glowing shell of gas called a planetary nebula. Despite the name, such nebulae have nothing to do with planets. The term arose because, through early telescopes, these gas shells looked like small, round disks. The planetary nebula shines for a few tens of thousands of years as the cast-off gas is illuminated by the hot white dwarf in its center. Eventually, the gas disperses into the interstellar medium, carrying with it the star's remaining outward material. The white dwarf then cools slowly over billions of years, fading gradually from white to yellow to red, and finally to a cold, dark black dwarf, essentially a cinder of a star. However, the universe is not old enough for any white dwarf to have cooled to a black dwarf yet. For a massive star, the finale is far more dramatic. A star, say 10 times the mass of the Sun, or more, will also exhaust its fuel. But its core's fate is different. In the late stages of a massive star's life, its core becomes layered like an onion with elements. Hydrogen fusing into helium in outer shells, helium into carbon in inner layers, and so forth, building up to iron in the core. Iron is the last stop. Fusion of iron doesn't release energy. When a massive star builds an iron core, it's a sign that the star's life has reached a critical point. With no more energy output from fusion, the iron core is overwhelmed by gravity and collapses in on itself in a fraction of a second. The imploding core then rebounds, triggering a titanic explosion, a supernova. In that instant, the star is destroyed in one of the most powerful events in the universe. The supernova can outshine an entire galaxy for a short time, blasting the star's outer layers into space at tremendous speeds. In the fiery crucible of this explosion, atoms are smashed together to create many of the heavier elements on the periodic table. Gold, silver, uranium, elements that were not formed during the star's quieter burning phases. These newly forged elements are ejected into space along with the stellar debris. What remains of the massive star's core after the explosion is an ultra-dense object. If the original star was moderately massive, say up to perhaps 20 times the Sun, the core compresses into a neutron star. A neutron star is an astonishing object. It packs more mass than the Sun into a sphere only about 20 kilometers across. To put that in perspective, a teaspoon of neutron star material would weigh about as much as a mountain on Earth. Neutron stars are so dense that their gravity warps space nearby and time itself slows relative to faraway observers. Many neutron stars spin rapidly and emit beams of radiation from their magnetic poles. If those beams sweep past Earth, we see pulses of light. Such neutron stars are observed as pulsars, flashing rhythmically like cosmic lighthouses. If the star was even more massive, above a certain threshold, not even the formation of a neutron star can halt the collapse. In those cases, the core collapses utterly, vanishing from view and forming a black hole. This is a region of space where the gravity is so intense that nothing, not even light, can escape from its immediate vicinity. The black hole's formation is the ultimate endpoint for the most massive stars, an object of almost inconceivable density and gravitational pull. We will soon explore these strange entities in more detail. In their depths, stars enrich the galaxy. The material blasted out by red giant winds or supernova explosions carries a treasury of heavy elements that were forged in those stars' cores. When that material mixes into the interstellar clouds, it seeds them with elements like carbon, oxygen, iron, the ingredients of planets and of life. New stars will form from this enriched matter, and around some of those stars, planets will coalesce, built from the recycled star stuff. In this way, each generation of stars hands down a chemical legacy to the next. Our own solar system, for instance, contains gold and uranium and other heavy elements that must have been created in one or more supernovae before the sun was born. It is often said, quite literally, that we ourselves are made of star stuff. The very atoms in our bodies were forged in previous generations of stars. Long ago, some ancient stars lived out their lives, created elements in their cores and in their explosive deaths, and sewed those atoms into the nebulae that would form new stars, new planets, and eventually us. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were once inside a star. When we look at the night sky, we are essentially looking at our cosmic ancestors. Understanding the life cycles of stars shows us the deep connection between our existence and the cosmos. Having followed a star from birth in a nebula to death as a white dwarf, neutron star, or black hole, we now turn to examine perhaps the most enigmatic of these outcomes: the black hole. Black holes and other cosmic mysteries push the boundaries of our knowledge and spark our imagination. In the next stage of our journey, we will venture into the realm of these dark mysteries of the universe. Few phenomena in astronomy are as mystifying and captivating as black holes. A black hole is the aftermath of gravitational collapse taken to the extreme. Imagine a mass so concentrated that the curvature of space around it becomes like a deep well. If anything, a star, a planet, or even a beam of light ventures too close, it can be pulled in and cannot escape again. The boundary of no return is called the event horizon. Once anything crosses that invisible line, it vanishes from the observable universe, trapped by the black hole's gravity. At the center of a black hole, according to general relativity, all the infalling mass is crushed to an infinitely dense point, known as a singularity. Our laws of physics, as we know them, break down under those conditions, rendering the singularity a great unknown. Black holes come in different scales. Some are formed from the collapse of massive stars and might weigh a few times the mass of the sun. These stellar mass black holes are scattered throughout galaxies, often unseen, except when they interact with nearby stars. In such cases, gas from a companion star can spiral into the black hole, heating up and emitting X-rays before crossing the horizon. This is one way astronomers detect these otherwise invisible objects. On the other end of the scale, there are supermassive black holes, with masses millions or even billions of times that of the Sun. Astonishingly, nearly every large galaxy, including our Milky Way, harbours a supermassive black hole at its centre. These giants may have formed from the merger of many smaller black holes and gas, or perhaps originated from direct collapse of huge primordial gas clouds in the early universe. Their exact origin remains an active area of research. At the Milky Way's core, as we noted, lies Sagittarius A, a black hole of about 4 million solar masses. Even larger ones are found in other galaxies. For example, the galaxy M87 contains a black hole weighing over 6 billion suns. These central black holes can profoundly influence their host galaxies. When they actively accrete matter, they can erupt as quasars or active galactic nuclei, shooting out jets of energy and radiation that can be seen across the universe. But when dormant, as ours currently is, they are quiet giants, detectable mainly through the gravitational dance of stars around them. In fact, it was by observing stars orbiting an unseen object at tremendous speeds near our galactic center that astronomers confirmed the presence of Sagittarius A. In recent years, humanity achieved a remarkable milestone. We captured the first direct image of a black hole's immediate vicinity. In 2019, using a network of radio telescopes around the globe, the Event Horizon Telescope, scientists produced an image of the supermassive black hole in galaxy M87, revealing a bright ring of light encircling a dark shadow, the imprint of the event horizon. A few years later, a similar technique yielded an image of Sagittarius A, our own galaxy's central black hole. These images confirmed that the predictions of general relativity hold true. We indeed saw the light being bent and swallowed by a gravity well, just as theory foretold. Despite these advances, black holes remain deeply mysterious. What lies beyond the event horizon? Does the singularity persist as an infinite point, or do new physics come into play? Some theories even speculate that a black hole could be a gateway, perhaps leading to a phenomenon called a white hole elsewhere, or even to another universe, or that it could spawn a baby universe inside. Such ideas remain in the realm of conjecture, but they underscore how black holes push our understanding to its limits. We do know that black holes are not cosmic vacuum cleaners, indiscriminately devouring everything. A black hole behaves like any other mass from a distance. If the Sun were replaced by a black hole of equal mass, Earth's orbit would remain unchanged, though we would lose sunlight. Up close, however, the extreme curvature of space makes for bizarre effects. Time near a black hole slows down relative to the outside universe. If one could watch an object falling in, it would appear to slow and fade, never quite crossing the horizon from our view, a trick of time dilation and light redshift. The reality for the infalling object, however, is swift and inexorable descent. Black holes also have given us a new way to observe the cosmos, through gravitational waves. When massive black holes collide, they unleash ripples in the very fabric of spacetime, propagating outward like the concentric waves from a pebble dropped in water. In September 2015, detectors on Earth, LIGO, directly measured such ripples for the first time, generated by the merger of two black holes in a distant galaxy. The signal was incredibly subtle, yet it opened a new window on the universe. We could hear the final moments of two black holes spiraling into each other and merging into a larger one, converting a portion of their mass into a fleeting burst of gravitational energy. This breakthrough confirmed a major prediction of Einstein's theory and marked the birth of gravitational wave astronomy. Now, we routinely detect these whispers from collisions of black holes and neutron stars, enriching our understanding of these exotic objects. As we probe such extremes, we also confront other grand mysteries of the cosmos, beyond the realm of immediate observation. One is the question of dark matter. When astronomers observe the way galaxies rotate, they find that the outer regions are moving faster than can be explained by the gravity of visible matter alone. Likewise, clusters of galaxies seem to have far more gravity than their luminous matter would suggest, bending background light more than expected. The solution that has emerged is that a vast amount of unseen mass permeates galaxies and clusters. We call this unknown mass dark matter. It neither emits nor absorbs light, making it invisible across the electromagnetic spectrum. Yet it exerts gravity. By current estimates, dark matter makes up about 27% of the universe's content, far outweighing the ordinary matter, the stars, gas, dust, planets, everything we can see, which accounts for less than 5%. Without dark matter, the formation of galaxies and the motions we observe simply would not make sense. What is dark matter? That remains unsolved. It might be an undiscovered type of subatomic particle, or a hidden aspect of gravity itself. Experiments underground and in space are attempting to detect traces of dark matter particles, so far to no avail. For now, dark matter is inferred only through its gravitational influence, a shadow presence that we map indirectly, like seeing the wind only through the swaying of the trees. If dark matter is a mystery of the tangible, albeit invisible, mass in the universe, an even more staggering enigma is dark energy, a mystery of the universe's expansion. In the late 20th century, observations of distant supernovae led to a shocking discovery. The expansion of the universe is accelerating. For decades, scientists assumed that the expansion, set in motion by the Big Bang, would be slowing down over time due to gravity. Instead, those distant exploding stars appeared dimmer than expected, indicating they were farther away than they should be, meaning the expansion has sped up during the billions of years their light traveled to us. To explain this acceleration, we invoke dark energy, which is thought to comprise roughly 68% of the universe. Dark energy seems to be a property of space itself, driving galaxies apart at an ever-increasing pace. We don't yet know what dark energy actually is. It could be linked to the energy of the vacuum, or a new field or force at work. It remains one of the biggest open questions in cosmology. These dark components, dark matter and dark energy, remind us that the vast majority of the cosmos is hidden from direct view. All the shining stars and galaxies, all the glowing nebulae and radiant quasars make up only a small fraction of what's out there. We are only beginning to illuminate the full contents of the universe. Each mystery we solve often leads to new questions. Yet, there is a profound serenity in facing the unknown. It means the story of the cosmos is far from fully written, and there are more wonders waiting to be discovered. As we contemplate black holes and ponder invisible matter and energy, it helps to step back and see the grand stage on which these dramas play out. That stage is the universe itself, populated with countless galaxies beyond our own. Our journey now shifts, focus to the broader cosmos, to the multitude of galaxies and the vast structure of the universe at large, as we continue our tranquil voyage through the stars. Our Milky Way, vast as it is only one member of a vast community. As we step back and widen our view, we see that galaxies fill the universe like islands in a cosmic sea. Some are solitary, but many are grouped together by gravity. Our Milky Way, for instance, is part of a small gathering called the Local Group, a collection of more than 50 galaxies bound loosely together. Among them is the Andromeda Galaxy, a spiral much like our own, located about 2.5 million light-years away. Andromeda is the closest spiral galaxy to us, and on a clear, dark night, it can be seen as a faint smudge of light with the naked eye. Over billions of years, Andromeda and the Milky Way are destined to drift closer and eventually merge, a slow cosmic dance that will produce a new, larger galaxy. But even our local group is just one cluster in a greater assembly. We reside on the outskirts of the Virgo supercluster, which itself is one limb of an even larger structure known as Laniakea, a colossal supercluster of galaxies spanning 500 million light-years. Galaxies themselves are as diverse as the stars they contain. There are elegant spiral galaxies with majestic arms like the Milky Way and Andromeda, and there are elliptical galaxies, vast swarms of stars shaped like smooth, featureless ovals, often the result of many mergers. Some galaxies are small and irregular, mere wisps of stars without clear structure. Dwarf galaxies, containing only millions of stars, swarm around larger galaxies like bees around a hive. In contrast, the largest galaxies can hold trillions of stars and span over 1 million light-years across. Many galaxies, especially young ones or those in collision, are prolific star makers, blazing with the light of newborn star clusters. Others are ancient and quiescent, their stars old and red, the fireworks of star formation having long faded. On the largest scales, galaxies are not scattered randomly. They form a grand tapestry. They congregate into groups and clusters, which in turn gather into superclusters. These superclusters are arranged in filaments and sheets, threading across space. Between these filaments lie enormous voids, regions with far fewer galaxies, stretching tens of millions of light-years across. This web-like arrangement of matter is known as the cosmic web. It is as if the universe has a vast, sponge-like structure, dense regions where hundreds of galaxies connect, and huge empty bubbles between. Our home supercluster is just one thread in this cosmic web. When astronomers map the positions of galaxies in large surveys, the pattern of the cosmic web emerges, reminiscent of neural networks or lace, on scales so immense that it defies full comprehension. The numbers associated with the greater universe are staggering. It is estimated that the observable universe, the portion of the cosmos we can potentially see, contains on the order of 1 trillion galaxies, if not more. Each of those galaxies, in turn, contains millions, billions, or even trillions of stars. Even a typical galaxy like our Milky Way, with a few 100 billion stars, is mind-bogglingly large. Yet in the cosmos, it is just one of many. If one were to try to count the stars in all those galaxies, the total would reach a number beyond easy naming. Astronomers estimate that there are more stars in the observable universe than there are grains of sand on all the beaches and deserts of Earth. The night sky we see from Earth, filled with thousands of stars to the naked eye, is an infinitesimal sample of what's truly out there. Every patch of sky, even the darkest bit with no visible stars, when observed with powerful telescopes, is found to be teeming with distant galaxies upon galaxies. The Hubble Space Telescope's deep field images famously revealed thousands of galaxies in a tiny speck of sky, suggesting the entire heavens above are richly populated if we only look deep enough. Looking across these immense distances is also akin to looking back in time. The light arriving from the farthest galaxies began its journey billions of years ago, long before Earth existed. When we observe a galaxy a few billion light-years away, we see it as it was a few billion years in the past. The most distant galaxies detected by our current telescopes are seen as they were perhaps 13 billion years ago, when the universe was in its infancy. Through these observations, we catch glimpses of the early universe building its first galaxies and stars. Peering far out in space, we watch the cosmic history unfold. Galaxies colliding and merging, star formation rates rising and falling, the gradual build-up of structure over cosmic time. It is remarkable that by simply collecting faint photons of light, we can reconstruct how the cosmos grew up from its younger days to the present majestic vista. Though our technology allows us to see billions of light years out, there is an edge to what we can observe. The observable universe is limited by the finite age of the universe, about 13.8 billion years, and the finite speed of light. We cannot see beyond a certain distance because the light from those regions has not had enough time to reach us. Beyond the farthest galaxies, we can see lies the ultimate background glow, the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. It is a uniform whisper of light, cooled to just a few degrees above absolute zero, filling the universe and marking the horizon of our vision. This primordial light is the oldest signal we can detect, a foggy curtain beyond which direct observation fails. What lies beyond that cosmic horizon, we can only imagine. Perhaps unending stretches of more galaxies, or perhaps an entirely different realm of reality. Standing here, figuratively at the edge of the observable universe, we find ourselves in awe of the grandeur of it all. Countless galaxies drift through the cosmic darkness, each an oasis of stars, perhaps with their own planets and possibilities. The universe, on the grandest scale we know, is both wondrous and humbling, an expanse with no known center, filled with structures we are just beginning to map. And yet, despite its vastness, it operates under the same natural laws that we have come to understand in part. Gravity, pulling galaxies into graceful dances. Light traveling across eons to connect us with far-flung corners of space. And the ongoing story of creation and transformation, written in the language of stars and galaxies. Our journey through the starry expanse has carried us from the quiet of interstellar space to the grand architecture of the cosmic web. We have floated among newborn stars in nebulae, witnessed the life and death of suns, and pondered mysteries that stretch the limits of our understanding. Through it all, a sense of calm and wonder pervades, a recognition of the vast, beautiful continuum of existence of which we are a part. As we drift onward, the cosmos stretches out infinitely before us, silent and serene. There is no final boundary to this voyage, for every horizon reveals another beyond it. In this tranquil cosmos, we continue our journey, content to bask in the starlight and the infinite possibilities of the universe, knowing that more wonders await as our exploration goes on. In the silent expanse of space, patterns and pulses quietly govern the cosmos. We drift onward in our celestial journey, sensing a gentle order in the darkness. Stars rise and set in cosmic time. Planets trace graceful paths around their suns. All move in quiet rhythm, as if the universe itself were composed of silent music. This subtle cosmic harmony has guided the dance of galaxies and atoms alike since the dawn of time. Ancient philosophers once imagined a music of the spheres, a celestial symphony produced by the motion of planets and stars. Though no sound reaches our ears in the vacuum of space, the idea lives on, that the cosmos has its own rhythm. Each planet circles its star with steady grace. Moons whirl around planets, and stars themselves orbit the center of their galaxies. These movements repeat over and over, like measures in an endless, silent song. Our own Earth spins on its axis, turning day to night and back again with comforting regularity. This daily spin sets the basic beat of life. Sunrise following every long night, a promise renewed each morning. At the same time, Earth travels around the sun once each year, bringing the progression of seasons. Spring follows winter, summer follows spring, in an ancient cycle that has guided life for eons. These celestial rhythms create the clock by which countless creatures eat, sleep, migrate, and thrive. Every world has its own tempo. A day on swift Mercury, closest to the Sun, lasts 2/3 of an Earth year, sunrise to sunrise stretching endlessly under its blistering sky. On Jupiter, a gas giant spinning rapidly, day and night flicker by in just 10 hours. Saturn's rings cast changing shadows as that planet tilts through its seasons. Each planet dances to a slightly different beat, yet all are part of the same cosmic orchestra, governed by gravity and time. From the shortest day to the longest year, these cycles weave a complex but harmonious cosmic rhythm. Above us, the moon dances around the Earth, completing a cycle roughly every month. As it waxes and wanes, we see its bright face change from a slim crescent to a full disk and back again. This lunar cycle pulls at Earth's oceans, orchestrating the rise and fall of tides. Ancient people watched the moon's phases and learned to measure time by its journey. Even now, the moon's gentle glow and regular rhythm inspire a sense of calm and wonder, a monthly reminder of cosmic order. Now and then, the celestial rhythms sync in special events. The moon glides precisely between Earth and Sun, casting a fleeting shadow and turning day into twilight, a solar eclipse. Planets occasionally line up in the sky, sharing a brief moment of alignment before continuing on their individual paths. Comets swing in from the outer reaches on long orbits, returning after decades or centuries to grace our skies. One famous comet, now known as Halley's Comet, appears roughly every 76 years and has been recorded throughout human history. Each of these events is a momentary chorus in the music of the spheres, a reminder of the vast cosmic clockwork ticking silently above. During a total solar eclipse, the moon perfectly covers the sun, and day plunges into an eerie twilight. Birds grow quiet, as if night had suddenly fallen. A hush sweeps over the world. Only the sun's corona, a halo of pearly light, is visible around the moon's silhouette. In those brief minutes, observers witness the grand clockwork of the heavens in action. Then, as the moon moves on, sunlight returns, and day is reborn. Such events, rare and fleeting, have always stirred awe, reminders of the precise cosmic choreography that guides our days. Even chaos in space often hides subtle harmony. Jupiter's largest moons, for instance, orbit in a resonant pattern. Io, Europa, and Ganymede are locked in a 1-2-4 rhythm, meaning for each orbit of Ganymede, Europa orbits twice and Io 4 times. With each lap, they tug on each other, but instead of disorder, they maintain a stable cadence that has lasted eons. Such resonances are nature's way of keeping time, as if the moons were playing chords in the Jovian system. Similar celestial resonances can be found throughout the cosmos, hinting that even amidst complexity, patterns emerge and endure. Beyond our solar system, rhythms continue on grand scales. Our Sun, with all its planets in tow, orbits the center of the Milky Way galaxy. One galactic year, a single journey around, takes roughly 200 million Earth years. In that time, mountains rise and wear away on Earth, species evolve and vanish. Yet the Sun keeps steadily circling, as countless other stars do, all bound in the graceful rotation of our spiral galaxy. On even larger scales, galaxies themselves can dance around each other, drawn together by gravity in slow stately orbits across billions of years. Stars, too, can be partners in a rhythmic dance. Many stars come in pairs or groups, orbiting a common center. Some twin stars circle so closely that from afar they appear as one, until their orbit makes one pass in front of the other, causing the combined light to dip and brighten in a regular pattern. Elsewhere, exotic stellar remnants, like pulsars, spin furiously, sending beams of radiation flashing like cosmic lighthouses. A pulsar's pulse can be more precise than any clock, ticking milliseconds with each rotation, the heartbeat of a dead star echoing through space. Even living stars sometimes keep time. Certain giant stars swell and shrink in slow cycles, growing brighter and fainter as if breathing. These stellar pulses might take days or weeks, a gentle throbbing in the starry night. Watching their reliable pattern from Earth, astronomers learn to gauge cosmic distances, using these pulsing stars as mileposts in the vastness. In the quiet cosmic night, every flicker carries meaning, every rhythm a message across space and time. These cycles in the heavens resonate subtly in the lives below. We humans, too, organize our days by the sun's light and rest under the night sky. Our bodies carry their own rhythms, the beating of our hearts, the flow of our breath, gentle oscillations that sustain us. It is as if the patterns of the cosmos echo within, reminding us that we are not separate from this cosmic dance. From the spinning of electrons in an atom to the whirling of galaxies, nature favors rhythm and repetition, weaving a cohesive melody through all things. If you lie beneath a clear sky and watch patiently, you can sense these rhythms playing out. The stars slowly wheel overhead as the hours pass, a testament to Earth's steady rotation. Night after night, the positions of the stars shift with the seasons. Familiar constellations of winter give way to the different stars of summer. The sky is like a giant clock face, with stars as its dial. By simply observing, you can tell the time of year and time of night from the canopy of heaven's slow dance. For millennia, humans have lived by these celestial clocks. Travelers of old navigated vast oceans by the stars, trusting the fixed northward glow of the pole star or the motion of constellations as their guide. Farmers planted and harvested by the timing of the sun and moon, guided by the reliable change of seasons. Festivals and calendars were built around solstices and equinoxes, points in Earth's orbit marked by the sun's rising and setting positions. The sky was humanity's first calendar and compass, its rhythms woven into our cultures and stories. Even the Earth's axis itself traces a slow circle in the sky, a wobble called precession. Over a cycle of about 26,000 years, the northward point of the axis drifts from one star to another. In ancient times, a different star guided northward journeys, and in the far future, yet another will take its place. This grand, slow-motion rhythm is imperceptible to a single human life, yet it is part of the cosmic dance that continues, regardless of our awareness. There is comfort in these grand routines. No matter what happens in our lives, the dawn will follow the night. The stars will circle overhead on schedule. The universe keeps a steady beat that outlasts our individual worries and moments. By recognizing this steady cadence in nature, people through the ages found reassurance and continuity. It is as if the cosmos offers a lullaby, a predictable rhythm that cradles us from birth to death, linking each generation under the same reliable sky. Even now, As you listen to these words, the cosmic rhythms continue unabated. Somewhere on Earth, the sun is rising, bringing morning light to end the night. On the opposite side of the planet, stars are emerging in dusk skies as evening falls. The same moon that our ancestors watched thousands of years ago will sail through tonight and tomorrow, and long after we are gone. Generations before us tracked these cycles, and generations after will do the same. These celestial rhythms bind together past, present, and future, a comforting reminder that in an ever-changing world, some patterns endure. All these rhythms, from the twirling of moons to the sweeping orbits of galaxies, compose a cosmic story. They mark the passage of time in the universe's own language. But how do we, on our tiny world, come to know this grand celestial music? The secret lies in the messengers that cross the darkness between the stars. In every beam of starlight and every cosmic ray is carried news of distant worlds and times long past. Through these silent messengers of light, we begin to understand time and space on a cosmic scale. Across the vacuum of space, a single photon of light streams silently toward us. It may have left its home star long before we ever existed, traveling for years, centuries, or millennia through the dark. Now, tonight, it ends its journey by touching your eye. In that brief moment, across unimaginable distance, you and a far-off star become connected. Such is the magic of light, a messenger carrying the story of a distant sun into the present moment, bridging time and space with a mere spark. Whenever we gaze at the stars, we are truly looking into the past. Because light, while incredibly fast, does not travel instantaneously. It takes time to cross the great gulfs between stars. The moonlight you see is a little over a second old. Sunlight is already 8 minutes old by the time it bathes dawn skies in gold. When you make a wish on a distant star, the light that grants you that view might have been on its way for hundreds or thousands of years before it meets your eyes. The farther away an object is, the longer its light has been in transit. The nearest stars beyond our sun lie a few light years away. Their glow started its journey before many of us were born. The light from the Andromeda galaxy, our nearest galactic neighbour, takes over 2 million years to reach us. That means we see Andromeda as it was when early humans were just beginning to walk the Earth. And for galaxies billions of light years away, we are seeing a ghost of the universe as it was eons ago, long before our planet even existed. Light's finite speed sets a limit on how fast even information can travel. Our galaxy alone is so vast that even a beam of light would take 100,000 years to cross it. To journey to the nearest large galaxy, Andromeda, would require over 2 million years at light speed. And the edge of the observable universe lies tens of billions of light years away, distances so great that light from those realms has been travelling almost the entire age of the universe to reach us. We live in a universe where vast distance and deep time are intertwined. In this way, telescopes become time machines. By capturing ancient light, we can look back into the history of the cosmos. When astronomers point our most powerful telescopes at distant galaxies, they are seeing those galaxies as they were billions of years ago. We collect faint whispers of light that left shortly after the universe's birth, allowing us to glimpse the cosmic dawn when the first stars and galaxies were forming. Each photon is a tiny piece of a story that began long before humanity, arriving now to illuminate our understanding. The oldest light of all is not from a star or a galaxy, but from the birth of the universe itself. We are bathed in a faint afterglow that fills all of space, the cosmic microwave background. This gentle radio hiss is the remnant of the first light released when the universe was only a few 100,000 years old. It has been traveling for nearly 14 billion years, stretched and cooled to microwaves we can only detect with sensitive instruments. It is a whisper from the dawn of time, carrying a portrait of the infant universe on its glow. Because of these vast light travel times, the cosmos we see is a mixture of present and past. Some of the stars twinkling above might no longer exist, having lived out their lives and faded or exploded eons ago. Yet their light, still crossing space, shows them alive to us tonight. In that sense, the night sky is like a time mosaic, each pinprick of light a different era reaching our eyes together. We are observers of many times at once, witnessing a silent film of the cosmos, frame by frame, as the universe reveals its story over ages. From time to time, the sky reminds us of this truth in dramatic ways. In the year 1987, a new pinprick of light appeared in the night sky of Earth's southern hemisphere. It was a supernova, a star exploding at the end of its life in a nearby dwarf galaxy. That star had actually died around 160,000 years before, long before humans had modern minds. But its light only reached Earth on that night in 1987, suddenly revealing the event to our eyes. It was a cosmic message in a bottle, arriving across millennia to tell the story of a star's final moment. In a way, the night sky is a living museum of cosmic history. Its nearest exhibits are stars of our own galaxy from the recent past. Further out, the faint smudges of galaxies are relics from an earlier time. Overhead, we simultaneously behold multiple eras of the universe. It's as though time has been frozen in those beams of light, allowing us to study ages long gone. Each star's light is a souvenir from a distinct moment, some from when our ancestors walked the earth, others from before our planet had formed. Under the stars, we are not just looking into space, we are peering into time itself. This relativity of time and distance works both ways. Imagine somewhere far across the galaxy, an observer looking back at Earth through a powerful telescope. If they are, say, 100 light years away, they would not see us as we are today, but as we were a century ago. Were they 1,000,000 light years away, they might see Earth in the time of our early ancestors, or see dinosaurs if they looked from tens of millions of light years. The universe keeps its secrets by distance, only revealing the past, never the present, to distant eyes. Light, of course, is more than what our eyes can see. The colours of the rainbow are only a tiny slice of a vast spectrum of electromagnetic waves. Invisible radio waves carry messages from pulsars and cold gas clouds. Infrared light reveals the warm glow of star-forming nurseries hidden behind dust. Energetic X-rays and gamma rays arrive from violent events like exploding stars and feeding black holes. Each band of light brings different information, like different voices in the cosmic conversation. By tuning into all these wavelengths, we enrich the story that light tells us about the universe. Along with light, other ghostly messengers traverse the cosmos. Neutrinos, nearly massless particles born in the hearts of stars and during supernovae, stream through space and even through solid planets as if they weren't there. Every second, trillions of them from our sun pass through your body unnoticed. In 1987, detectors deep underground caught a handful of neutrinos from a supernova in a nearby galaxy, hours before its visible light reached Earth. These nearly invisible particles had escaped the exploding star's core and raced ahead, heralding the star's death. It was another way the universe spoke to us, whispering its events through multiple channels. And light is not the only cosmic messenger. In recent years, we have begun to detect faint ripples in the fabric of space itself, gravitational waves. When massive objects like black holes collide or stars explode asymmetrically, they send out vibrations that travel across the universe at the speed of light. These ripples are unimaginably small when they reach us, but with delicate instruments we can sense them. For the first time, humanity has heard the universe tremble. It is as if we have added a new sense, feeling the shiver of distant cosmic events, not just seeing their light. In 2015, we finally heard such a cosmic ripple for the first time. Two black holes merging in a distant galaxy sent out waves that gently jiggled instruments on Earth by less than the width of an atom. The signal arrived as a faint, rising chirp, the dying song of that distant merger. It lasted only a fraction of a second, yet from it, scientists confirmed a prediction of Einstein and opened a new era of astronomy. It was humbling to realize that an event over 1 billion light-years away could reach us not through light, but through the stretching of space itself. A subtle vibration felt across the cosmos. Within the light that reaches us are hidden clues encoded by nature. When we split starlight into a spectrum, we reveal faint lines, as unique as fingerprints, that tell us what elements a star or galaxy contains. Subtle shifts in those lines show if an object is moving toward us or away, letting us measure the dance of stars and the expansion of space itself. From these delicate details of light, we have learned many cosmic secrets: how stars are born and die, how galaxies grow, and how the universe evolves over time. Piece by piece, these messengers, light and other cosmic whispers, have allowed us to assemble the history of the universe. They guide us, like celestial storytellers, back through time. Through them, we witness the birth of stars and galaxies, the spread of light in darkness, and the transformation of the cosmos across billions of years. Following their trail leads us to the ultimate questions. How did all of this begin? How did we come to be here? The answers lie in the story of origins, a story written in the cosmos itself and echoed in every atom of our being. At the very dawn of time, the universe burst into existence. In an unimaginable flash of energy and light, everything that would ever be was condensed in a single, primal point. Time and space themselves began in that moment. As the newborn cosmos expanded, it was filled with a blinding brilliance. The early universe was a searing ocean of particles and light, so hot and dense that atoms could not yet form. There was no distinction of stars or galaxies, just a luminous fog slowly stretching outward, cooling and dimming as it grew. As the minutes and hours passed in this infant universe, it expanded rapidly and began to cool. Particles joined to form the simplest atoms, hydrogen and helium. The intense glow gradually softened. After about 380,000 years, space had expanded enough that light could finally travel freely without being trapped by matter. The brilliant fireball of creation faded into a gentle glow. The cosmos went dark to human eyes, an age before any star had yet shined. Only the faint afterglow of that first light remained, filling space with a quiet whisper of what had been. In the darkness that followed, the universe was like a deep night awaiting its first dawn. No stars or galaxies existed yet, only immense clouds of primordial gas drifting through expanding space. For millions of years, the cosmos was dark and still, but not idle. Gradually, gravity began to gather the gas into denser pockets. These pockets grew, drawing more matter inward, heating up under the pressure of their own weight, until, at last, one of them ignited. After perhaps 100 million years or more, the first stars were born, and the cosmic night was broken by starlight. This was the cosmic dawn, the moment the universe lit up with the very first stars. They clustered in proto-galaxies, bringing light to the darkness for the first time. These first stars were giants, burning their fuel quickly and living short, brilliant lives. In their hearts, they forged heavier elements: carbon, oxygen, nitrogen, seeds of future worlds and life. When those massive pioneers exhausted their fuel, they died in spectacular explosions, supernovae, that scattered their enriched guts back into space. The darkness returned briefly, but the ingredients for a more complex cosmos were now in place. With each generation of stars, the universe grew more varied and rich. Those first supernovae seeded the cosmic gas with new elements, which then formed later stars and young galaxies. Over hundreds of millions and then billions of years, galaxies took shape: spirals, ellipses, clusters of countless suns swirling together. In one such developing galaxy, in a quieter corner of the cosmos, a spiral of stars and gas was forming, our Milky Way. Within its arms, new stars continued to spark to life, each generation carrying more of the heavy elements forged by those that came before. About 4.6 billion years ago, in one of the Milky Way's spiral arms, a giant cloud of gas and dust began to collapse. Perhaps the shockwave of a nearby supernova helped kickstart it. At its center, pressure and heat grew until a new star ignited: our Sun. Around that newborn sun, the remaining gas and dust formed a wide disk. Over time, in that disk, particles clumped together into pebbles, then boulders, then planetesimals. In this cosmic nursery, the planets were born. Closest to the Sun, the inner planets emerged as rocky worlds, including a blue planet we call Earth. In Earth's infancy, a violent collision likely occurred. A Mars-sized protoplanet grazed the young Earth. The impact tore off a portion of Earth's molten mantle and flung it into orbit. Over time, this debris coalesced into our Moon. The Moon's presence would come to stabilize Earth's wobbling tilt, moderating the seasons and tides. Even in these chaotic early days, as molten rock and dust danced around the newborn planet, the stage was being set for a stable home where life could take root. The Moon thus became Earth's constant companion, a lasting souvenir of the turbulent process of planetary birth. Earth began as a molten sphere, battered by constant impacts in a young, chaotic solar system. Over time, it cooled and developed a solid crust. Water collected in basins to form the first oceans, whether delivered by icy comets or emerging from within the Earth itself. Thick clouds and rains helped create a temperate surface. In those early waters, under a young sun, a remarkable thing occurred: the spark of life. Simple organic molecules, energized by sunlight and lightning, assembled into structures that could grow and replicate. From these humble beginnings, the story of life on Earth commenced. In these primeval waters, under flickers of lightning and sunlight, something extraordinary took place. Simple molecules that had formed in the young oceans began to link together, forming more complex structures. Perhaps around a warm volcanic vent, or in a sunlit tidal pool, chemistry crossed a threshold into biology. A tiny self-copying molecule assembled, the first seed of life. In time, this gave rise to the first living cell, a simple membrane-bound droplet that could grow and divide. It may have been humble and microscopic, but it was the genesis of all life to come. For billions of years, life remained in the seas, small and simple. Single-celled organisms floated in the waters, slowly transforming the planet. Some learned to harness sunlight, releasing oxygen into the oceans and sky. In time, the atmosphere became rich enough in oxygen to support new kinds of life. Multi-celled organisms emerged, and around 540 million years ago, life underwent a great proliferation of forms in the seas. Jellyfish drifted through ancient oceans, trilobites scuttled on seabeds, and the first primitive fish appeared. Strange plants and fungi colonized the shorelines as life ventured onto land, preparing the way for forests and land animals to follow. Earth's history was punctuated by upheavals, mass extinctions that ended entire lineages in a geological instant. Yet life proved remarkably resilient. After each crisis, new forms emerged, filling the world with fresh diversity. Even the disappearance of the dinosaurs cleared the stage for mammals to thrive and diversify. In time, among those mammals, on the great savannas of Africa, a new kind of animal appeared, one with curious eyes that turned upward to the stars. Our early human ancestors had arrived, the latest branch on a very old tree of life, carrying the spark of awareness. From those early hominids, eventually came modern humans. Our species, Homo sapiens, is only about 200,000 years old, a blink of an eye in cosmic time. Yet in that short span, we learned to make tools, to paint images on cave walls, and to tell stories around the fire. We formed languages to share our thoughts, and passed knowledge from generation to generation. By the time we began building cities and civilizations, the night sky had already captivated us for millennia. We were drawn to those points of light, filled with wonder, asking the eternal questions. What are those lights? How did we come to be under them? What is our place in this vast cosmos? Unbeknownst to those first stargazers, the stars were not just distant lights, but kin. The very elements in our bodies, the calcium in our bones, the iron in our blood, the carbon in our cells, were forged long ago in stellar furnaces. We are made of star stuff, born from the ashes of ancient suns. It took the entire history of the universe to shape us. The Big Bang created the raw materials, the stars transmuted those into the elements of life, and countless cosmic events paved the way for our Earth to form and life to blossom. We are, quite literally, children of the cosmos. It is astonishing how many cosmic coincidences paved the way for us. If any detail had changed, if a vital star had not exploded to seed our region with heavy elements, if our sun had formed too early or too late, if Earth hadn't acquired water, the chain leading to our existence could have been broken. Yet, against the odds, the conditions aligned. In the immense reaches of time and space, a planet formed with all the right ingredients, and life took hold and grew more complex until consciousness emerged. In the grand cosmic unfolding, we are a rare and precious outcome. To grasp the vastness of cosmic time, Imagine compressing the entire 14 billion year history of the universe into a single year. In this cosmic calendar, the Big Bang occurs at the first moment of January 1st. The Milky Way forms around March. Our solar system appears in early September. Life on Earth emerges by late September. Dinosaurs roam the Earth on December 25th and vanish on December 30th. Modern humans only arrive in the final hour of New Year's Eve. And all of recorded human history flashes by in the last seconds of December 31st. Such is the brevity of our existence against the backdrop of cosmic time. And yet, within those fleeting seconds, we have begun to understand the whole grand year that came before us. Our awareness is a recent phenomenon, but it is a product of the universe itself. Through us, the cosmos can reflect on its own existence. We are a way for the universe to know itself, an eye through which the cosmos gazes back at the stars. Having arisen from the cosmic process, we turned our minds toward understanding that process. The journey of life had led to curious and intelligent beings capable of unraveling the very story that produced them. And thus began humanity's journey, explorers of the cosmic ocean on a voyage of discovery, imagination, and wonder. Human curiosity about the cosmos is as old as our species. Our early ancestors, gathered around fires under the stars, wove stories and myths to explain the lights overhead. They imagined heroes and monsters drawn in the patterns of the constellations. Each sunrise, each eclipse, each comet that graced the sky became part of their lore. The night sky was a grand tapestry of mystery and meaning. By watching the heavens, they learned when to sow crops or hunt migrating herds, guided by the seasonal positions of stars. In these ways, the sky became our first textbook and calendar. Under the vault of stars, our ancestors also found their way across unknown lands and seas. Polynesian voyagers, for example, navigated the vast Pacific Ocean using nothing but the stars, sun, and ocean swells as guides. They memorized the rising and setting points of specific stars to chart canoe courses over thousands of miles, finding tiny islands in the great dark sea. In the northern hemisphere, travelers relied on the steady glow of the North Star to orient themselves. The night sky was their map and compass when all else was featureless ocean or desert. In learning the language of the heavens, early explorers extended the reach of humanity across the earth. Across different civilizations, humans built structures aligned with the heavens. Stone circles, pyramids, and temples tracked the sun's solstices and the moon's cycles. Ancient astronomers in China, Mesopotamia, and Greece mapped the stars and noted the wandering planets. They began to seek patterns and predict celestial events. By careful observation, they learned to forecast eclipses and the return of comets. Such knowledge was powerful and almost magical, a sign that we could decipher the sky's code. Bit by bit, we were learning the true rhythms of the cosmos and our place within it. One can still witness the importance of these rhythms in ancient monuments. At Stonehenge in England, on the summer solstice, the rising sun perfectly frames a doorway of massive stones, just as its builders intended 5,000 years ago. In Central America, Maya temples were designed to cast serpent-like shadows on equinox days, marking planting and harvest times. Across the world, from the pyramids of Egypt to the medicine wheels of North America, our ancestors built in harmony with the sky. These structures, still standing, speak to a deep human need to connect with the cosmos and mark our place in the dance of time. For a long time, we assumed Earth was the center of all things. The sun, moon, and stars seemed to circle us, and it felt natural to believe the cosmos was built around our tiny world. But as our observations grew more precise, cracks in that view emerged. Half a millennium ago, bold thinkers proposed that Earth was not the center, but instead a planet orbiting the Sun like any other. This idea was met with resistance and wonder. It was a profound shift in perspective. Our home was just one world among many, moving through a far larger cosmos. The invention of the telescope opened our eyes wider than ever. Suddenly, the moon was revealed to have mountains and craters, another world with landscapes. Jupiter was seen to carry its own moons, tiny points of light orbiting a giant planet. The Sun revealed blemishes, sunspots, drifting across its face, showing that even stars had their imperfections and rotation. All these discoveries in the 17th century confirmed that the heavens were not unchanging crystal spheres, but places we could study and understand. The cosmos began to feel closer, its secrets more within reach of human inquiry. With each advancement, our understanding deepened. We discovered physical laws, like gravity, that govern both an apple falling to Earth and the moon circling Earth. The same forces acting on our world were at work among the stars. As science grew, we realized the stars were incredibly distant suns, and our sun was one star among billions in a vast galaxy. The Milky Way's cloudy band was resolved into countless stars. And in the 20th century, we learned our galaxy was just one island in a universe of innumerable galaxies, all drifting within the expansion of space. The universe had grown immeasurably larger in our minds. We also found clues to our own cosmic origin. In the 1960s, radio antennas picked up a faint hiss coming uniformly from all directions in space, the remnant glow of the primordial fireball that gave birth to the universe. This cosmic microwave background, as it's called, was like an echo from the Big Bang. Its discovery confirmed that the universe had a beginning and has been evolving ever since. In a way, we had tuned in to the universe's memory of its infancy. The story of creation that had once only been myth was now being read in the very light of the cosmos. The yearning to explore eventually carried us beyond our home planet. In the mid-20th century, we developed rockets powerful enough to break the bonds of Earth's gravity. Our first emissaries were simple satellites that orbited Earth, followed by animals and then humans. In 1961, a human being left Earth's atmosphere for the first time, orbiting the planet and gazing down on the blue horizon of home. Just 8 years later, in 1969, humanity set foot on the moon. As an astronaut stepped onto the lunar surface, he looked back at the distant Earth, a fragile blue marble suspended in darkness, and forever changed our perspective of home. For a moment, humanity was united in awe, witnessing what had once seemed impossible become reality. The sight of humans moving on the moon's desolate plain and the words spoken from that 250,000 miles away echoed across Earth. Many who watched felt a shift inside, a realization that if we could voyage to another world, even one so near, then all of us on Earth were linked in that extraordinary endeavor. The moon landing was not just a scientific triumph, but a poetic one. It fulfilled ancient dreams and inspired new generations to look upward and continue seeking the unknown. After the moon, our robots took up the exploration. We sent robotic probes to other planets, extending our senses outward. Spacecraft flew past Jupiter and Saturn, sending back dazzling images of their swirling clouds and rings. We drove rovers across Mars's dusty plains, searching for signs of ancient water. One by one, our mechanical explorers have visited all the major worlds of our solar system. Voyagers 1 and 2 sailed beyond the outer planets, photographing giant worlds and moons, then continued on toward the edge of interstellar space. They carry with them golden records, human greetings and songs, in case some distant civilization ever finds these tiny ambassadors drifting in the void. Voyager 1 is now over 14 billion miles away, sailing through the emptiness between the stars. Yet decades after its launch, we can still hear its faint signal, a distant beacon from humanity. That golden record attached to its side carries the sounds of our planet: whale songs, human greetings in many languages, laughter and music. It's a time capsule of who we were when we sent it. One day, eons from now, perhaps some other beings will find Voyager drifting and learn about us. Or maybe it will wander forever, a silent ambassador of Earth. Either way, its journey reminds us how far our curiosity has taken us, from wondering at the stars to sending artifacts into the galactic sea. We also built observatories to peer deeper into the cosmos. The Hubble Space Telescope, once lofted above our atmosphere, revealed a universe of breathtaking beauty. Star nurseries wrapped in colourful nebulae, and galaxies in the act of collision. It even found unimaginable numbers of galaxies scattered across what seemed like empty space. In one tiny patch of sky that looked dark to our eyes, Hubble discovered thousands of distant galaxies, proving that even the emptiest sky teems with worlds. The scale of the universe grew again in our understanding, filling us with awe at its vastness and grandeur. More recently, new eyes like the James Webb Space Telescope have begun to capture the faint glow of the earliest galaxies that formed after the cosmic dawn. These instruments also let us probe the atmospheres of planets orbiting other stars, sniffing for signs of water or life. We have confirmed that the night sky is filled with exoplanets, distant worlds beyond our solar system, thousands of them and counting. Some of these planets may have conditions not unlike Earth's. Each discovery brings the cosmos a little closer, turning points of light into places we might one day know. As our tools grew more powerful, we began to not only look outward, but also listen. Radio telescopes tuned in to the sky's natural static, hoping to catch a whisper from another intelligent civilization. So far, the stars have kept their silence, but the possibility that we are not alone lingers in our minds. We scan the atmospheres of exoplanets for hints of life and send our own signals and probes into the void. In our quest to explore the cosmic ocean, we carry with us a hopeful question. Is there anyone else out there looking up at the same stars and wondering about us? We have even established a continuous presence beyond Earth. The International Space Station orbits high above, a laboratory where crews from many nations live and work together, floating in microgravity as they circle the globe. From that vantage, astronauts look down at Earth's continents and weather systems, experiencing sunsets and sunrises every 90 minutes. Their daily life is a reminder that humanity can adapt to space, if only in small ways so far. Each mission teaches us more about living off our planet, preparing us for journeys farther out, perhaps back to the moon, onto Mars, and one day beyond. In just a few millennia, we evolved from gazing at the sky from our doorsteps to actually reaching out and touching the heavens. Our journey through the cosmic ocean is still only beginning. We have waded just knee-deep from the shore of our home planet. Yet with every step, every discovery and every mission, we venture farther. We carry the indomitable curiosity that drove our ancestors, now aided by science and technology, pushing the boundaries of the known. As we sail among the stars in our minds and in our machines, we continue a story that began when the first human looked up in wonder. Amid all these achievements, one insight stands out. In exploring other worlds, we rediscovered our own. From space, our Earth appears breathtaking and fragile. The farther we ventured, the more we came to cherish the pale blue dot we call home. This journey through the vastness brought into focus the rarity and beauty of our planet and the unity of those who inhabit it. Now, with a cosmic perspective earned through centuries of exploration, we turn back toward our home world with a deeper sense of connection and responsibility. It is time to come home. Imagine you are far from Earth, perhaps standing on the dusty grey surface of the moon. Above the horizon, a blue-white sphere rises. Earth, glowing with life against the black void. This was the sight that Apollo astronauts witnessed. Our planet, hanging in the emptiness, breathtaking and delicate. From that distance, no borders or human divisions are visible. Only swirling clouds, blue oceans, and brown-green lands united under a fragile atmosphere. In the silence of the moon's shadow, they saw Earth as one whole, an oasis of life in a vast cosmic sea. That image forever changed how we see ourselves. Years later, as one of our spacecraft, Voyager 1, was preparing to leave the solar system, we turned it back to snap a last photograph of Earth. In that picture, taken from billions of miles away, Earth appears as a tiny speck of light, a pale blue dot suspended in a sunbeam. From that remote vantage, our planet is almost too small to notice. Everything we are, everything we have ever known, is contained in that single point of light. All our joys and sorrows, every king and peasant, every young couple in love, every mother and father, every life is lived out on that tiny stage, floating in the cosmic dark. Such a perspective can be deeply humbling and profoundly enlightening. Seen from afar, the endless conflicts and boundaries that separate us fade away. All that matters is that pale blue dot, our shared home, the only haven we know in an immense and possibly empty cosmic ocean. It underscores the truth that we are one family, living on one delicate world. The responsibility to cherish and care for our planet becomes clear when we view Earth from this distance. The atmosphere that sustains us is but a thin veil around that tiny orb. The biosphere, all of life, is an exquisite and fragile film on its surface. We realize that our fate and the fate of this world are inseparable. Astronauts often describe what's known as the overview effect, a profound shift in awareness when seeing Earth from space. They speak of a deep sense of unity among all people and a renewed appreciation for the beauty and fragility of our world. Problems that once seemed big become small and solvable when viewed against Earth's borderless panorama. Such reflections began in orbit, but they belong to us all. We don't have to travel to space to feel this change in perspective. Simply contemplating our planet from afar as a single blue marble can remind us of our common bond and shared destiny. Despite finding thousands of planets around distant stars, we have yet to find another quite like Earth. At least, not one whose oceans and forests we can see, or whose life we can detect. Our planet remains, as far as we know, a rarity, a world vibrant with life in a universe that, for all its immense size, has revealed no other living oasis so far. This could change with future discoveries. But either way, it reminds us how extraordinary our home is. The pale blue dot is not only our home, it may be uniquely blessed, a garden in the cosmic desert, deserving of our deepest care. After journeying through the cosmos in our minds, we return to find that home was beautiful all along. We carry with us the gift of perspective. On a warm night, when we look up from our backyards or balconies, we see the familiar stars with new eyes. We recognize that while we felt small under the vast sky, we are also part of that sky. The elements in our bodies were forged in distant stars, and the light in our eyes is kin to the light from galaxies. We belong here in this universe, not as insignificant strangers, but as offspring of the cosmos, connected to it in every way. If you ever find yourself beneath a truly dark sky, the Milky Way arches overhead, a pale river of starlight. You are looking edge-on into our home galaxy, seeing the combined glow of billions of distant suns. For most of human history, people saw this band and created legends about it. A path of spilled milk of a goddess, or the backbone of night. Now we know it is our galaxy's disk, and within it, nestled among countless stars, lies our sun and earth. When you gaze at that misty band, you are observing the structure that cradles us, a reminder that even on Earth, we reside inside the grand cosmic system we have explored in our minds. There is a profound peace in this realization. Knowing that we are an intimate part of the universe can bring comfort. The sense that we have an origin and a place in the grand scheme. The cosmos is no longer a cold, distant expanse, but a living context for our existence. The stars that wheel overhead each night are our extended family. Their story is our story. When we feel alone or troubled, we can step outside under the night sky and remember that we are part of something vast and meaningful. In the gentle twinkling of the stars, we can find solace and perspective. Coming home from our cosmic journey, we also find renewed appreciation for the simple rhythms of Earth, the cycle of day and night, which once seemed mundane, now feels like part of a universal pattern. We notice the golden light of dawn and the soft glow of dusk with greater reverence, knowing that countless worlds across the galaxy experience their own versions of daybreak and twilight. We feel the gentle tug of the moon on the tides and see it as a reminder of our connection to the wider cosmos, our own planet's music, the whisper of the wind, the patter of rain, harmonizes with the celestial music of the spheres we have imagined among the stars. The journey through time and space has brought us back to where we started, but we are not the same as when we began. We return with a quiet mind and a heart full of wonder. The universe has etched its story into us. We have seen how time flows from the first atoms to our beating hearts, how light connects distant epochs to the present, and how life emerged from stardust to contemplate the stars. We have traced the arc of existence and discovered that our own reflection can be found in the cosmos. The knowledge of this grand connectedness settles within us like a gentle cosmic lullaby, easing our fears and awakening awe. Imagine a far future generation, perhaps thousands of years from now, standing under these same stars. They might know far more about the universe than we do now. Perhaps they will voyage among the stars themselves. Yet no matter how advanced they become or how far they travel, the sight of the Milky Way across the night and the gentle rising of the sun will still inspire in them the same feelings of wonder and belonging. Some things in the human heart, awe, curiosity, the love of home, are as constant as the rhythms of the heavens. As long as there are people, the sky will continue to call to us, and we will answer. Under the eternal night sky, we find our place and our peace. The cosmos, once an unfathomable mystery, now feels like home in its own way. As we end this journey, we carry with us the quiet wonder of starlight, the ancient lullaby of the universe that has always been playing. In the stillness, you can almost hear it, the music of the spheres, a gentle, harmonious reminder that we are part of something greater. Our voyage through the tranquil cosmos comes to a close, but its reflections remain in our hearts. We return to our lives knowing that, whenever we need perspective or comfort, we can look up at the stars, remember this journey, and feel the calm of the cosmic embrace. We are home.